Hello there, and welcome to the Sleepy Science channel. Tonight, we will be exploring our closest star, the Sun, a blazing sphere of light and energy that has warmed our world for billions of years. The Sun is not just a distant ball of fire in the sky. It is the heart of our solar system, the source of all life on Earth, and a window into the nature of stars throughout the universe. Above us during the day, it appears as a bright disk, familiar and constant. But there is so much more than meets the eye. The Sun is a fusion reactor, a magnetic dynamo, and a cosmic timekeeper, all in one. It has shaped our planet's climate, guided ancient civilizations, and continues to influence every moment of our existence. If you enjoy these quiet explorations, I invite you to like and subscribe, or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the warmth of the Sun's story to carry you gently into sleep. Let's begin. The Sun is our closest star. The Sun sits at the center of our solar system, a glowing sphere of hydrogen and helium. To us, it appears larger and brighter than any other star in the sky. This is not because it is the most powerful or the largest star in the universe. Far from it. The Sun is actually quite average in the grand scheme of things. Its brilliance comes from proximity. At roughly 93 million miles away, it is our nearest stellar neighbor. The next closest star, Proxima Centauri, lies more than 4 light-years distant. That means the Sun's light reaches us in just 8 minutes and 20 seconds, while light from the next nearest star takes over 4 years to arrive. To ancient peoples, the Sun was often seen as a deity. Cultures around the world worshipped it, built monuments aligned to its movements, and organized their lives around its daily journey across the sky. The Egyptians called it Ra. The Greeks named it Helios. The Aztecs honored Tonatiuh. Each civilization recognized the Sun's vital importance, even if they did not understand its true nature. To them, it was not just a source of light and warmth, but the very heartbeat of existence itself. Today, we know the Sun is a star, one of hundreds of billions in our galaxy alone. Yet its closeness makes it unique to us. It is the only star we can study in detail, the only one whose surface we can see, and the only one whose influence we feel every single day. When you step outside and feel the warmth on your skin, you are experiencing energy that began its journey in the Sun's core, traveled through layers of plasma, and finally crossed the void of space to reach you. That warmth is older than you realize, forged in nuclear fire millions of years before it ever touched your face. The Sun is a middle-aged star. Stars, like living things, have life cycles. They are born, they mature, and eventually, they die. The Sun is currently in what astronomers call its main sequence phase, the long, stable period when a star fuses hydrogen into helium in its core. This process has been ongoing for about 4.5 billion years. The Sun is roughly halfway through its life, making it a middle-aged star. It has existed longer than complex life on Earth, longer than the dinosaurs, longer even than our planet's oldest rocks. When the Sun first ignited, Earth was a molten world, still forming from the debris of the early solar system. Over billions of years, the Sun remained steady, providing the consistent energy needed for life to emerge and evolve. It has been our constant companion through ice ages and warm periods, through the rise and fall of countless species, through every moment of human history. The pyramids were built under this same Sun. Ancient forests grew in its light. Every ancestor you have ever had lived beneath its glow. The sun will continue shining in much the same way for another 5 billion years or so. During that time, it will remain remarkably stable, giving humanity and all life on Earth a long future under its steady warmth. But nothing lasts forever. Eventually, the hydrogen fuel in its core will run low, and the sun will begin to change. It will swell into a red giant, growing so large that it may consume the inner planets, possibly even Earth itself. Its outer layers will drift away, leaving behind a small, dense core called a white dwarf. That remnant will slowly cool over trillions of years, fading into darkness. But that distant future is unimaginably far away. For now, the sun is in its prime, stable and steady, a reliable source of light and life. To think of the sun as middle-aged is strangely comforting. It reminds us that even stars have lifespans, that everything changes, but also that we live in a time of stability. The sun's middle age is our golden age. The sun contains 99.8% of the solar system's mass. When you think of the solar system, you might imagine planets, moons, asteroids, and comets, all drifting through space together. But the truth is, the sun dominates. It contains 99.8% of all the mass in the entire solar system. Jupiter, the largest planet, holds most of the remaining mass, while everything else, Earth included, is just a tiny fraction of the total. If you were to gather all the planets, moons, asteroids, and comets together, they would still be dwarfed by the sun's immense bulk. This overwhelming gravitational presence is what keeps everything in orbit. The sun's gravity reaches out across billions of miles, holding planets in their paths and shaping the structure of the solar system. Without it, the planets would drift away into interstellar space, untethered and lost. The sun is the anchor, the center around which everything else revolves. Even distant objects in the Oort cloud, trillions of miles away, still feel its pull. The sun's mass is so great that it creates a deep well in the fabric of space-time itself. This is not just metaphorical. According to Einstein's theory of general relativity, mass warps space, and the sun's mass creates a curvature that planets follow as they orbit. They are not being pulled by an invisible string, but rather gliding along the curves of space-time, shaped by the sun's presence. It is a cosmic dance, elegant and eternal, governed by gravity's gentle hand. To realize that the sun contains nearly all the mass of everything we consider our cosmic neighborhood is humbling. We live on a tiny speck orbiting a giant, and that giant is itself just one star among countless others. Yet for us, it is everything. It is home base, the gravitational heart of our world. The sun is a giant nuclear reactor. At the sun's core, temperatures reach around 15 million degrees Celsius. Under such extreme heat and pressure, hydrogen atoms collide with such force that they fuse together, forming helium. This process, called nuclear fusion, releases tremendous amounts of energy. Every second, the sun converts about 600 million tons of hydrogen into helium. In doing so, it loses about 4 million tons of mass, which is transformed into energy according to Einstein's famous equation, E equals mc squared. That energy radiates outward from the core, traveling through the sun's interior in a journey that can take hundreds of thousands of years. Photons, particles of light, are created in the core and begin their slow migration toward the surface. They do not travel in straight lines. Instead, they bounce and scatter, absorbed and re-emitted countless times as they make their way through the dense plasma. By the time a photon finally escapes the sun's surface and streams into space, it may have been traveling for over 1 million years. The energy we receive from the sun today began its journey long before humans existed. The light that warmed the dinosaurs started in the sun's core when Earth was a very different place. The sunlight that touches your face right now is ancient, a relic of processes that occurred deep within the sun's heart eons ago. Yet it feels immediate, warm, and present. That is the paradox of sunlight. It is both old and new, both distant and intimate. Nuclear fusion is the reason the sun shines. It is the force that powers all stars, transforming matter into light and heat. Without it, the universe would be cold and dark, a lifeless void. Fusion is creation at its most fundamental level, the forging of new elements from simpler ones, the birth of energy from matter. The sun is not burning like a fire. It is fusing, transmuting, and radiating. It is a cosmic alchemist, turning hydrogen into helium and mass into the energy that sustains life. The sun's surface is called the photosphere. When we look at the sun, we are not seeing its interior. We are seeing its surface layer, called the photosphere. This is where the sun's light escapes into space, giving us the bright disk we observe in the sky. The photosphere is only a few hundred kilometers thick, a thin shell compared to the sun's vast interior. Yet it is the boundary between the hidden depths and the visible universe, the place where light is set free. The temperature of the photosphere is around 5,500 degrees Celsius, far cooler than the core, but still hot enough to vaporize any known material. If you could somehow stand on the photosphere, which you cannot because it is not a solid surface, you would be instantly incinerated. The photosphere is a seething layer of plasma, with rising and falling currents creating a textured appearance. Through telescopes, astronomers see granules, bright cells of hot plasma rising from below, surrounded by darker lanes where cooler plasma sinks back down. These granules are enormous, each one about the size of Texas, yet they appear and disappear within minutes. The sun's surface is constantly churning, a dynamic and ever-changing landscape. Sunspots also appear on the photosphere. These are cooler, darker regions where strong magnetic fields inhibit the flow of heat from the interior. Sunspots can be larger than Earth itself, and they come and go in cycles, growing more numerous and then fading away over roughly 11 years. Ancient observers noticed these dark blemishes and wondered what they were. Some thought they were planets crossing the sun's face. Others believed they were omens. Today, we know they are windows into the sun's magnetic activity, clues to the complex forces at work beneath the surface. The photosphere is the sun's face, the part we see and measure. It is the boundary between the star's hidden interior and the light that fills our solar system. Every sunrise, every sunset, every ray of sunlight that reaches Earth originates from this thin, glowing layer. To gaze at the sun, even indirectly, is to look upon the photosphere, the luminous skin of our closest star. The sun's atmosphere extends far beyond its visible surface. Above the photosphere lies the sun's atmosphere, a region that extends millions of miles into space. The first layer is the chromosphere, a thin region just above the photosphere. It glows with a reddish hue, visible only during solar eclipses when the moon blocks the bright light of the photosphere. The chromosphere is hotter than the photosphere, reaching temperatures of around 20,000 degrees Celsius. This increase in temperature moving away from the sun's surface seems counterintuitive, but it is driven by magnetic fields and shock waves that carry energy upward. Above the chromosphere is the corona, the sun's outer atmosphere. The corona is a marvel of extremes. It extends millions of miles into space, creating a tenuous halo of plasma around the sun. Its temperature soars to over 1 million degrees Celsius. sometimes reaching several million degrees. Yet, despite this intense heat, the corona is incredibly faint. Its density is so low that if you could somehow exist within it, you would not feel the heat in the same way you would in a hot room. There simply are not enough particles to transfer energy efficiently. The corona is only visible from Earth during a total solar eclipse, when the moon blocks the photosphere and reveals the delicate, wispy structures surrounding the sun. These structures are shaped by magnetic fields, creating loops, arcs, and streamers that stretch far into space. Ancient observers who witnessed eclipses were awed by the corona's appearance, often describing it as a crown or halo. The word corona itself means crown in Latin, a fitting name for this glowing atmosphere. Why the corona is so much hotter than the layers beneath it remains one of the great mysteries of solar physics. Researchers have proposed various mechanisms, including magnetic reconnection and wave heating, but the exact process is still being studied. The Sun's atmosphere is a place of complexity and beauty, where magnetic forces sculpt the flow of plasma and energy, cascades upward in ways we are only beginning to understand. Solar winds stream constantly from the Sun. The Sun does not just radiate light, it also sends out a constant flow of charged particles, a stream of electrons and protons that rushes through the solar system at speeds of hundreds of kilometers per second. This is the solar wind, and it carries the Sun's influence far beyond the visible glow of its surface. The solar wind originates in the corona, where the high temperatures give particles enough energy to escape the Sun's gravity and race outward into space. The solar wind is not uniform. It varies in speed and density, sometimes flowing gently, other times surging in powerful gusts. During periods of high solar activity, when sunspots and solar flares are common, the solar wind can intensify, carrying bursts of energy and particles toward Earth and the other planets. These gusts can interact with planetary magnetic fields, creating beautiful auroras, and, in extreme cases, disrupting satellites and power grids. The solar wind fills the Heliosphere, a vast bubble of space around the Sun where its influence dominates. This bubble extends far beyond the orbit of Pluto, reaching out more than 10 billion miles. At its edge, the solar wind slows and mingles with the interstellar medium, the thin gas that fills the space between stars. The boundary of the heliosphere is called the heliopause, and only a few human-made spacecraft, the Voyager probes, have crossed it, venturing into true interstellar space. To think of the Sun as sending out a wind, a constant breeze of particles, is a reminder that stars are not static, they are dynamic, active, and constantly interacting with their surroundings. The solar wind is the Sun's breath, an exhalation that reaches across the solar system and touches every planet, moon, and asteroid in its path. The Sun's magnetic field is complex and ever-changing. Beneath the Sun's glowing surface lies a powerful magnetic field, generated by the motion of plasma in its interior. The Sun rotates, but not as a solid body. Different parts rotate at different speeds. The equator spins faster than the poles, completing a rotation in about 25 days, while the poles take closer to 35 days. This differential rotation twists and tangles the magnetic field, creating loops, arcs, and concentrations of magnetic energy. These magnetic structures rise through the photosphere, creating sunspots, solar flares, and coronal mass ejections. Sunspots form where strong magnetic fields break through the surface, inhibiting convection and cooling the plasma locally. Solar flares are sudden releases of magnetic energy, explosions of light and radiation that can outshine the entire Sun at certain wavelengths. Coronal mass ejections hurl billions of tons of plasma into space, carrying magnetic fields along with them. The Sun's magnetic field flips roughly every 11 years. During this cycle, the number of sunspots waxes and wanes. At solar maximum, the Sun is covered with spots, and solar activity is high. At solar minimum, the Sun appears almost spotless, and activity is low. This 11-year cycle has been observed for centuries, and it influences space weather, auroras, and even subtle effects on Earth's climate. The magnetic field also shapes the corona, creating the loops and streamers visible during eclipses. It channels the solar wind, accelerating particles along magnetic lines and sending them out into the solar system. The Sun's magnetism is not just a detail of its physics, it is a fundamental part of its character, shaping its appearance, its activity, and its influence on the space around it. Sunspots were observed by ancient astronomers. Long before telescopes, people noticed dark spots on the Sun. Chinese astronomers recorded sunspots as early as 800 before Common Era, describing them as blemishes or marks on the Sun's face. Ancient Greeks and Romans occasionally noted them as well, though many believed the Sun should be perfect and unblemished, leading some to explain the spots as planets crossing in front of the Sun. It was not until the early 1600s, with the invention of the telescope, that sunspots were studied in detail. Galileo Galilei was among the first to observe them through a telescope, sketching their positions and noting that they moved across the Sun's surface, proof that the Sun itself rotated. This was a radical idea at the time. Many believed the heavens were unchanging, perfect spheres turning in eternal harmony. The discovery of sunspots challenged that notion, showing that even the Sun was subject to change. Over the centuries, astronomers tracked sunspots and discovered their cycles. The 11-year pattern became clear, and researchers began to understand that sunspots were tied to magnetic activity. In the 1800s, astronomer Richard Carrington observed a massive solar flare erupting from a sunspot group, and shortly afterward, Earth experienced intense auroras and disruptions to telegraph systems. This was the first direct evidence that the Sun's activity could affect our planet. Today, sunspots are monitored constantly by observatories around the world and satellites in space. They are windows into the Sun's magnetic heart, indicators of solar activity, and predictors of space weather. These dark blemishes, once seen as imperfections, are now understood as vital clues to the Sun's nature. To gaze at a sunspot is to see magnetism at work, to witness the dynamic processes that make our star so much more than a simple glowing sphere. Solar flares release energy equivalent to millions of nuclear bombs. When magnetic energy builds up in the Sun's atmosphere, it can release suddenly in an event called a solar flare. These explosions are among the most powerful events in the solar system, releasing energy equivalent to millions of nuclear bombs detonating at once. In just a few minutes, a solar flare can emit as much energy as the Sun normally radiates in hours. The light from a flare spans the electromagnetic spectrum, from radio waves to X-rays and gamma rays, flooding the solar system with radiation. Solar flares can affect Earth in various ways. The burst of X-rays ionizes the upper atmosphere, disrupting radio communications. High-energy particles can damage satellites, harm astronauts in space, and create auroras at lower latitudes than usual. During particularly strong flares, power grids on Earth can be affected, and in extreme cases, transformers can be damaged, leading to widespread blackouts. The most intense solar flare ever recorded occurred in 1859, known as the Carrington event. It sent auroras as far south as the Caribbean and caused telegraph systems to fail, with some operators receiving electric shocks. If a flare of that magnitude struck today, the impact on our technology-dependent world would be significant. Satellites, GPS systems, and power grids could all be affected, reminding us how connected we are to the sun's behavior. Despite their power, solar flares are not dangerous to life on Earth's surface. Our atmosphere shields us from the radiation, absorbing the harmful X-rays and particles before they can reach the ground. But in space, astronauts and satellites are more vulnerable. Understanding solar flares and predicting them is an important part of space weather forecasting, helping to protect our technology and explorers beyond Earth's protective atmosphere. Solar flares are reminders of the sun's raw power. They show us that our star is not a placid, unchanging orb, but a dynamic, energetic force capable of sudden outbursts. Yet for all their violence, they are also part of the sun's natural rhythm, moments when magnetic energy seeks release and the star's hidden forces become briefly visible. Coronal mass ejections hurl plasma across the solar system. Even more dramatic than solar flares are coronal mass ejections, or CMEs. These events occur when the sun ejects enormous clouds of plasma and magnetic fields into space, sometimes hurling billions of tons of material outward at speeds of several million miles per hour. A CME can take hours to unfold, slowly lifting off the sun and expanding as it travels through the solar system. When aimed at Earth, a CME can take 1 to 3 days to arrive, giving us some warning before it impacts our planet's magnetic field. When a CME reaches Earth, it can compress the magnetosphere, triggering geomagnetic storms. These storms energize particles in Earth's magnetic field, sending them cascading into the atmosphere near the poles, where they create stunning auroras. But they can also induce electric currents in power lines, pipelines, and other long conductors, potentially causing damage. In 1889, a powerful geomagnetic storm caused auroras visible as far south as the tropics and set telegraph paper on fire in some offices. CMEs are driven by the same magnetic forces that create sunspots and solar flares. When magnetic field lines on the sun become twisted and stressed, they can snap and reconfigure, releasing energy and flinging plasma into space. The sun's corona is constantly in motion, and CMEs are part of its dynamic behavior. They are not aimed at Earth specifically. Most CMEs shoot off in other directions, missing our planet entirely. But when one does head our way, it is a reminder of how interconnected we are with the sun. Studying CMEs helps scientists understand not just the sun, but space weather as a whole. Predicting when a CME will occur and whether it will impact Earth is a challenge. But satellite observations and computer models have improved our ability to forecast these events. As humanity ventures farther into space, understanding CMEs will become even more important. Ensuring the safety of astronauts and the reliability of technology beyond Earth's protective magnetic shield. The sun rotates, but not as a solid body. If you watch sunspots over several days, you will notice they move across the sun's face, carried by the star's rotation. But the sun does not rotate like a solid ball. Because it is made of plasma, different parts rotate at different speeds. The equator spins faster, completing a rotation in about 25 days, while regions closer to the poles take 30 to 35 days. This is called differential rotation, and it is common among stars. This differential rotation has profound effects on the sun's magnetic field. As the equator spins faster than the poles, magnetic field lines get stretched and twisted, like winding up a rubber band. Over time, this twisting creates complex magnetic structures that rise to the surface, forming sunspots and active regions. Eventually, the magnetic field becomes so tangled that it reconfigures, flipping the sun's magnetic poles. This process takes about 11 years, and it drives the solar cycle. The interior of the sun is divided into layers, and each layer rotates at its own speed. Deep in the core, where fusion occurs, the rotation is slow and steady. In the radiative zone, energy slowly percolates outward through countless interactions. In the convective zone, hot plasma rises, cools, and sinks in vast rolling currents, carrying heat toward the surface. These convective motions, combined with rotation, create the sun's magnetic field through a process called the dynamo effect. Understanding the sun's rotation and its effects on magnetic activity helps scientists predict solar weather and understand other stars. Many stars rotate faster than the sun, especially young ones, and their magnetic activity is correspondingly more intense. As stars age, they slow down, and their magnetic fields weaken. The sun's rotation is a window into its life story, a clock ticking through billions of years, marking time in cycles of magnetic activity and surface motion. The sun's core is the hottest part. At the very center of the sun lies its core, a region spanning about a quarter of the sun's radius. Here, temperatures reach around 15 million degrees Celsius, and the pressure is immense, about 250 billion times the atmospheric pressure at Earth's surface. Under these extreme conditions, hydrogen nuclei, which are simply protons, collide with enough force to overcome their natural repulsion and fuse together, forming helium. This fusion process releases energy in the form of gamma-ray photons and fast-moving particles called neutrinos. The neutrinos escape almost immediately, passing through the sun as if it were not there, streaming out into space at the speed of light. Some of these neutrinos pass through Earth and through you every second, trillions of them, barely interacting with anything. Detecting these solar neutrinos has been one of the great achievements of modern physics, confirming our understanding of what powers the sun. The gamma-ray photons, however, do not escape so easily. They are absorbed and re-emitted countless times, scattering through the dense plasma of the sun's interior. This process can take hundreds of thousands to over 1 million years. By the time the energy finally reaches the surface, it has been transformed many times over, shifting from gamma rays to X-rays to ultraviolet to visible light, the sunlight we see and feel. The core is the heart of the sun's power, the place where matter is converted into energy and the forces of nature play out on the smallest scales. Without the core's fusion reactions, the sun would collapse under its own gravity and life on Earth would never have begun. The core is hidden from view, buried beneath layers of plasma and light, but its influence is felt throughout the solar system. Every photon that warms Earth's surface began its journey there, in the unimaginable heat and pressure of the sun's fiery heart. Energy takes hundreds of thousands of years to escape the sun. When a photon is created in the sun's core, it begins what seems like a simple journey outward. But the sun's interior is incredibly dense, filled with countless particles that absorb and scatter light. Each time a photon is absorbed by an atom, it is quickly re-emitted, but in a random direction. This process repeats over and over, creating a chaotic path called a random walk. The photon bounces around, sometimes moving outward, sometimes inward, sometimes sideways, slowly making its way toward the surface. Scientists estimate this journey through the sun's radiative zone takes anywhere from 100,000 to more than 1 million years. Think about that for a moment. The light that touches your skin today began its journey before humans evolved, before modern civilizations arose, before recorded history began. It is ancient light, carrying energy from fusion reactions that occurred when Earth was a very different place, perhaps during the time of early hominids or even earlier mammals. After fighting its way through the radiative zone, the photon enters the convective zone, where heat is transported by massive currents of rising and sinking plasma. Here, the journey speeds up. Hot plasma carries the energy toward the surface in a matter of weeks or months. Finally, the photon reaches the photosphere and escapes into space, free at last. From there, it takes just 8 minutes and 20 seconds to reach Earth, completing a journey that spanned eons within the Sun. This incredible time delay means the Sun has an enormous reservoir of energy already in transit. Even if fusion in the core were to suddenly stop, the Sun would continue shining for hundreds of thousands of years as the stored energy slowly worked its way out. The Sun is like a vast battery, holding energy in light's long journey from core to surface. It is a reminder of the scale and complexity hidden within our seemingly simple, steady star. The Sun loses mass every second. Through fusion, the Sun converts mass into energy. Every second, about 600 million tons of hydrogen are fused into roughly 596 million tons of helium. The missing 4 million tons are converted into energy. Following Einstein's equation, E equals mc squared. That energy radiates outward as light, heat, and particles streaming into space. In addition to mass lost through fusion, the Sun also sheds mass through the solar wind, sending charged particles racing into the solar system. 4 million tons per second may sound like an enormous amount, and it is, but compared to the Sun's total mass, it is a tiny fraction. The Sun weighs about 2 times 10 to the power of 30 kilograms, a number so large it is difficult to grasp. At the current rate of mass loss, the Sun could shine for billions of years without significantly diminishing. Over its entire main sequence lifetime, it will lose only a small percentage of its total mass, nowhere near enough to threaten its stability. This mass loss is actually a gentle process. Unlike explosions or violent events, the Sun's conversion of mass to energy is smooth and continuous. It has been happening for 4.5 billion years, and it will continue for another 5 billion years or so. The Sun is slowly, steadily radiating itself into space, turning matter into the light that illuminates our world. Every ray of sunshine is a piece of the Sun that has been transformed and set free. It is humbling to think that the warmth of sunlight is the Sun itself, converted from matter into energy and sent across 93 million miles to reach us. When you feel the Sun on your face, you are feeling a star's essence, a piece of its being transformed and delivered across the void. The Sun gives itself to the solar system, constantly, quietly, without fanfare, and in doing so, it sustains life, warms worlds, and shapes the very structure of space around it. The Sun is about 4.5 billion years old. Our Sun, along with the solar system, formed approximately 4.6 billion years ago from a vast cloud of gas and dust. This cloud, called a molecular cloud or nebula, was mostly hydrogen, with traces of helium and heavier elements created by earlier generations of stars. Something triggered the cloud's collapse, perhaps a shockwave from a nearby supernova, and gravity took over. The cloud began to spin and flatten into a disk, with most of the mass falling toward the center. As material accumulated at the center, the pressure and temperature increased. Eventually, the core became hot enough for nuclear fusion to ignite. The Sun was born. Around it, the remaining material in the disk coalesced into planets, moons, asteroids, and comets, forming the solar system we know today. This process took tens of millions of years, a blink of an eye in cosmic terms, but an unimaginably long time for us. The Sun's age has been determined through multiple methods. One is radiometric dating of meteorites, ancient rocks that formed in the early solar system and have remained largely unchanged. By measuring the decay of radioactive isotopes within them, scientists can calculate their age and, by extension, the age of the Sun. Another method involves studying the Sun's composition and comparing it to models of stellar evolution. All lines of evidence point to an age of about 4.6 billion years. 4.5 billion years is almost incomprehensible. It is longer than the age of the oldest rocks on Earth, longer than life has existed on our planet, longer than the formation of the Moon. The Sun has been shining steadily for all that time, through the formation of Earth, the rise of life, the evolution of complex organisms, and the entire history of humanity. It is our ancient companion, older than the ground beneath our feet, older than the oceans, older than the air we breathe. The Sun will shine for another 5 billion years. The Sun is roughly halfway through its main sequence lifetime. For the next 5 billion years or so, it will continue fusing hydrogen into helium in its core, shining much as it does today. This stability is what makes life on Earth possible. Stars that vary wildly in brightness or temperature would create chaotic conditions for any planets orbiting them. The Sun's steadiness is a gift, providing a consistent source of energy for billions of years. However, nothing lasts forever. Eventually, the hydrogen in the Sun's core will run low. When that happens, the core will contract and heat up, and fusion will begin in a shell around the core. The Sun will start to swell, its outer layers expanding outward. It will become a red giant, growing so large that it may engulf Mercury, Venus, and possibly Earth. The surface will cool and glow with a reddish hue, but the Sun will be far more luminous than it is today, radiating hundreds of times more energy. During its red giant phase, the Sun will fuse helium into carbon and oxygen in its core. This phase will be much shorter than its time on the main sequence, lasting only a few 100 million years. Eventually, the Sun will shed its outer layers in a series of pulses, creating a beautiful planetary nebula, a glowing shell of gas expanding into space. At the center will remain the Sun's core, now a white dwarf, a dense, hot ember slowly cooling over trillions of years. By the time this happens, humanity will either have long since vanished, evolved into something unrecognizable, or migrated to other star systems. The Earth of that distant era will be uninhabitable, scorched and barren. But for now, we live in the Sun's golden age, when it is stable, bright, and life-giving. We are fortunate to exist during this long, peaceful period, basking in the light of a star in its prime. The Sun's light takes 8 minutes to reach Earth. The Sun is about 93 million miles, or 150 million kilometers, away from Earth. Light travels incredibly fast, at roughly 186,000 miles per second, or 300,000 kilometers per second. At that speed, light from the Sun takes approximately 8 minutes and 20 seconds to reach us. This means that when you look at the Sun, you are seeing it as it was 8 minutes ago, not as it is right now. This time delay has interesting implications. If the Sun were to suddenly vanish, which it will not, we would not know for over 8 minutes. For that brief period, we would continue to see the Sun shining, feel its warmth, and experience daylight, all while the Sun was already gone. Only after 8 minutes would darkness fall, and the Earth would begin to drift out of its orbit, no longer held by the Sun's gravity. Of course, the Sun is not going anywhere. It is stable and will remain so for billions of years. But the 8-minute light travel time is a reminder of the distances involved in space. Even our closest celestial neighbor, the Sun, is far enough away that light takes time to bridge the gap. The Moon is much closer, only about 1.3 light seconds away. Mars, at its closest, is over 3 light minutes away. As we look farther into the solar system and beyond, the light travel times grow longer, and we peer deeper into the past. This delay also affects space exploration. Signals sent to spacecraft traveling through the solar system take minutes or even hours to arrive, depending on the distance. Controllers on Earth must plan ahead, sending commands that will not be executed until much later, and waiting patiently for responses that take just as long to return. The speed of light, though unimaginably fast by human standards, imposes limits on how quickly we can communicate across the vast distances of space. Sunlight provides the energy for nearly all life on Earth. Almost every living thing on Earth ultimately depends on the sun for energy. Plants, algae, and certain bacteria perform photosynthesis, capturing sunlight and using it to convert carbon dioxide and water into glucose and oxygen. This process is the foundation of most food chains. Plants are eaten by herbivores, which are in turn eaten by carnivores. Even organisms that live in darkness, such as deep-sea creatures, often rely on organic matter that sinks from the sunlit surface where photosynthesis occurs. There are a few exceptions. Some ecosystems, like those around deep-sea hydrothermal vents, rely on chemosynthesis, where bacteria use chemical energy from the Earth's interior instead of sunlight. But these are rare. The vast majority of life, from the smallest plankton to the largest whales, traces its energy back to the sun. Every bite of food you eat, every breath you take, is connected to the sun's light. The oxygen in the air was produced by photosynthesis. The energy in your cells came from food that, at some point, was created using sunlight. In a very real sense, we are all solar-powered. Our bodies run on energy that originated in the sun's core, was carried outward as light, traveled across space, and was captured by plants on Earth. The sun is not just a distant star. It is the ultimate source of the energy that keeps us alive. Without it, Earth would be a frozen, lifeless world, dark and silent, drifting through the void. This connection is ancient. For billions of years, the sun has fueled life on Earth. The first photosynthetic organisms appeared over 3 billion years ago, and they began transforming the planet, producing oxygen and paving the way for complex life. The sun has been the silent partner in evolution, the constant presence that made everything possible. Every leaf, every tree, every blade of grass is a tiny solar panel, capturing the sun's light and turning it into life. The sun appears larger at sunrise and sunset. When the sun is near the horizon, either at dawn or dusk, it often appears larger than when it is high in the sky. This is an optical illusion known as the moon illusion, which also affects how we perceive the sun. There is no physical change in the sun's size. It is the same distance away and subtends the same angle in the sky regardless of its position. But our brains, influenced by the presence of foreground objects like trees, buildings, and the landscape, interpret the low sun as being farther away and therefore larger. This illusion has puzzled observers for centuries. Ancient philosophers and astronomers noticed it and tried to explain it. The true cause is still debated, but it seems to be a perceptual effect, a quirk of how our visual system processes distance and size. When the sun is high overhead, there are no reference points, and it appears smaller. When it is on the horizon, surrounded by familiar objects, our brain adjusts its perception, making it seem larger. Sunrises and sunsets are also times when the sun's light passes through more of Earth's atmosphere. This scatters shorter wavelengths of light, like blue and green, leaving the longer wavelengths, reds and oranges, to dominate. The result is the beautiful colors we associate with dawn and dusk. The sun itself does not change color. It is always a white star, emitting light across the spectrum. But our atmosphere filters and scatters that light, painting the sky with hues that shift as the sun moves. To watch a sunrise or sunset is to witness the interplay of light, atmosphere, and perception. It is a daily reminder of the sun's presence, a moment when its beauty is most apparent. For thousands of years, humans have paused to watch the sun rise and set, marking the passage of time and feeling a connection to the rhythms of the cosmos. These moments are fleeting, but they anchor us to the larger cycles of day and night, of Earth's rotation and the sun's steady light. Ancient cultures built monuments aligned to the sun. Long before modern science, ancient civilizations recognized the sun's importance and built structures aligned to its movements. Stonehenge in England is perhaps the most famous example. On the summer solstice, the longest day of the year, the sun rises directly over the heel-stone, aligning with the monument's central axis. This precise alignment suggests that the builders had a deep understanding of the sun's annual path across the sky. In Egypt, the Great Pyramids at Giza are aligned with cardinal directions, and certain shafts within them point towards specific stars and the sun's path. The Temple of Karnak has an axis aligned with the winter solstice sunrise. In Central America, the Maya built pyramids and observatories oriented to solar and astronomical events. At Chichen Itza, during the equinoxes, the setting sun creates a shadow pattern on the steps of El Castillo that resembles a serpent descending the pyramid. In the Americas, the ancestral Puebloans of Chaco Canyon constructed buildings with windows and markers that aligned with solar events. At Machu Picchu in Peru, the Intihuatana stone, whose name means hitching post of the sun, was used to mark the solstices and equinoxes. Across the world, from Newgrange in Ireland to Angkor Wat in Cambodia, ancient peoples built monuments that tracked the sun, celebrating its cycles and using it to mark time. These structures were not just functional, they were sacred, expressions of reverence for the sun and its life-giving power. The sun governed the seasons, determined when to plant and harvest, and marked the passage of years. To ancient peoples, it was divine, and their monuments were ways of honoring it, connecting the earthly and the celestial. Today, these alignments still function, allowing us to stand where our ancestors stood and witness the same solar events they observed thousands of years ago. The sun's light is white, not yellow. If you ask someone what color the sun is, they might say yellow or orange, but the sun actually emits white light, a blend of all visible colors. When sunlight passes through a prism, it splits into a rainbow of colors, from red to violet, showing the full spectrum. The sun's surface temperature, around 5,500 degrees Celsius, makes it a white star, similar to how heated metal glows white when hot enough. So why does the sun often appear yellow or orange? The answer lies in Earth's atmosphere. When sunlight enters the atmosphere, it interacts with air molecules, which scatter shorter wavelengths like blue and violet, more than longer wavelengths like red and yellow. This scattering is why the sky appears blue. The scattered blue light is redirected in all directions, filling the sky with color. Meanwhile, the direct sunlight we see has less blue, making it appear more yellow. When the sun is low on the horizon, its light passes through more atmosphere, and even more blue light is scattered away. This makes the sun appear orange or even red at sunrise and sunset. But if you were in space, above Earth's atmosphere, the sun would appear white, its true color unfiltered. Astronauts and images from space missions show the sun as a brilliant white orb, not the yellow disk we see from the ground. Understanding the sun's true color is a reminder of how our perception is shaped by our environment. The atmosphere that shields us and gives us air to breathe also colors the light we see, painting the sky and tinting the sun. It is a beautiful partnership, one that creates the familiar blue skies and golden sunsets we cherish. The sun itself is white, but through Earth's lens, it becomes a palette of colors, shifting with the time of day and the angle of light. The sun contains most of the elements in the solar system. When the sun formed, it incorporated the material from the molecular cloud that gave birth to the solar system. That cloud contained hydrogen and helium, the most abundant elements in the universe, along with traces of heavier elements like carbon, nitrogen, oxygen, iron, and others. These heavier elements were created by previous generations of stars, forged in their cores, and scattered into space when those stars died. The sun contains roughly 73% hydrogen and 25% helium by mass, with the remaining 2% made up of heavier elements. This mixture reflects the composition of the universe as a whole, shaped by billions of years of stellar evolution. The heavier elements in the sun and in us were created in the hearts of long-dead stars, making us all, quite literally, stardust. By studying the sun's spectrum, astronomers can identify the elements present in its atmosphere. Each element absorbs and emits light at specific wavelengths, creating a unique signature. By analyzing the sun's light, scientists have identified over 70 elements in the solar atmosphere, from hydrogen to uranium. This technique, called spectroscopy, has been applied to other stars as well, revealing their compositions and helping us understand stellar evolution. The sun's composition also tells us about the history of the galaxy. Stars that formed earlier, when the universe was younger, have fewer heavy elements because there had been fewer generations of stars to create them. The sun, formed about 4.5 billion years ago, has a moderate amount of heavy elements, placing it in a generation of stars that includes many others like it. By studying the sun, we learn not just about our own star, but about the processes that shape galaxies and the universe. The sun's gravity holds the solar system together. Gravity is the force that binds the solar system. The sun's immense mass creates a gravitational pull that reaches out across billions of miles, keeping planets, asteroids, comets, and other objects in their orbits. Without the sun's gravity, these bodies would fly off into interstellar space, untethered and lost. The solar system exists because the sun holds it together, a cosmic anchor at the center of everything. The strength of gravity decreases with distance, following the inverse square law. This means that objects farther from the sun feel less gravitational pull. Mercury, the closest planet, experiences a much stronger pull than Neptune, the farthest. But even Neptune, billions of miles away, is still bound to the sun, completing an orbit once every 165 years. The sun's influence extends even farther into the Kuiper belt and the Oort cloud, regions filled with icy bodies that mark the outer edges of the solar system. Gravity also shapes the orbits of planets. Most planets follow nearly circular paths, but some, like Mercury and Pluto, have more elliptical orbits. Comets often have highly elongated orbits, swinging in close to the sun before retreating to the outer reaches. All these paths are dictated by gravity, the invisible force that governs motion in space. Isaac Newton first described the laws of gravity, showing how the same force that makes an apple fall also keeps the moon in orbit and the planets circling the Sun. Einstein later refined our understanding with his theory of general relativity, showing that gravity is not just a force, but a curvature of space-time itself. The Sun's mass warps the fabric of space, and planets move along the curves created by that warping. This elegant description reveals gravity as a fundamental property of the universe, shaping not just the solar system, but galaxies, clusters of galaxies, and the large-scale structure of the cosmos. The Sun's gravity is a reminder that we live in a universe bound together by forces that stretch across immense distances, connecting everything to everything else. Solar eclipses occur. When the Moon passes in front of the Sun, a solar eclipse is one of nature's most spectacular displays. It occurs when the Moon passes directly between the Earth and the Sun, casting a shadow on our planet. Because the Moon's orbit is tilted slightly relative to Earth's orbit around the Sun, eclipses do not happen every month. They are relatively rare, occurring only when the alignment is precise. There are three types of solar eclipses: partial, where the Moon covers only part of the Sun; annular, where the Moon is farther away and appears smaller, leaving a ring of sunlight visible; and total, where the Moon completely covers the Sun's disk. Total solar eclipses are breathtaking events. As the Moon slowly moves in front of the Sun, daylight dims, temperatures drop, and the sky takes on an eerie twilight. Animals may become confused, thinking night is falling. Birds stop singing, and some settle into roosts. Then, at totality, the Sun's corona becomes visible, a delicate halo of light surrounding the dark silhouette of the Moon. Stars and planets appear in the darkened sky. For a few precious minutes, the world is transformed. The fact that total solar eclipses are possible at all is a cosmic coincidence. The Sun is about 400 times larger than the Moon, but it is also about 400 times farther away. This means that from Earth, they appear almost the same size in the sky. No other planet in our solar system experiences such perfectly matched eclipses. On Mercury or Venus, the Moon would appear far too small to cover the Sun. On Mars, its moons are tiny and irregular, creating only small transits, not true eclipses. However, this perfect alignment will not last forever. The Moon is slowly drifting away from Earth at a rate of about 1.5 inches per year. In a few 100 million years, it will be too far away to completely cover the Sun, and total solar eclipses will no longer occur. We live in a fortunate time, a narrow window in Earth's history when the Sun and Moon appear the same size, creating one of the universe's most beautiful phenomena. Ancient astronomers could predict eclipses. Long before the advent of modern science, ancient astronomers discovered that eclipses follow patterns. The Babylonians, through centuries of careful observation, noticed that eclipses recur in cycles. One such cycle, known as the Saros cycle, lasts about 18 years, 11 days, and 8 hours. After this period, the Sun, Earth, and Moon return to roughly the same relative positions, and an eclipse, similar to one that occurred a Saros ago, will happen again. By tracking these cycles, Babylonian astronomers could predict when eclipses would occur, a remarkable achievement given their limited tools. In ancient China, astronomers also kept detailed records of eclipses, dating back over 3,000 years. These records were considered important for political and religious reasons. An unexpected eclipse was seen as a bad omen, while a predicted one demonstrated the emperor's harmony with the heavens. Chinese astronomers became skilled at forecasting eclipses, using mathematical models to calculate their timing. One legend tells of two court astronomers, Hai Sai and Ho, who were executed for failing to predict an eclipse, though this story is likely more myth than history. The ancient Greeks, too, were fascinated by eclipses. The philosopher Thales of Miletus is said to have predicted a solar eclipse in 585 before Common Era, though it is unclear exactly how he did so. Later, Greek astronomers like Hipparchus and Ptolemy refined eclipse predictions, developing geometric models of the sun's and moon's motions. The ability to predict eclipses was not just a scientific triumph, it was a demonstration of humanity's growing understanding of the cosmos, a proof that the heavens followed laws that could be discovered and understood. Today, we can predict eclipses with extraordinary precision, calculating their paths, years, or even centuries in advance. But the fundamental knowledge began with ancient observers who watched the sky with patience and curiosity, keeping records and noticing patterns. Their work laid the foundation for astronomy as a science, showing that the universe is not capricious, but orderly, governed by principles that reveal themselves to those who seek them. The sun's corona is only visible during total solar eclipses. The sun's corona, its outer atmosphere, is a place of mystery and beauty. It extends millions of miles into space, forming a tenuous halo around the sun. Despite its high temperature, often exceeding 1 million degrees Celsius, the corona is incredibly faint. Its light is only about 1/millionth as bright as the photosphere, the sun's visible surface. This means that under normal circumstances, the corona is completely overwhelmed by the sun's glare and cannot be seen. During a total solar eclipse, however, the moon blocks the bright photosphere, and the corona becomes visible. It appears as a delicate, pearly glow surrounding the dark silhouette of the moon, with streamers and loops extending outward. The shape of the corona changes with the solar cycle. During solar maximum, when the sun is most active, the corona is more symmetrical and evenly distributed. During solar minimum, it has prominent streamers near the equator and more compact structures near the poles. For centuries, astronomers could only study the corona during the brief moments of a total eclipse. These rare opportunities were precious, and expeditions were organized to travel to remote locations to observe eclipses and study the corona. In the 19th century, scientists discovered that the corona's spectrum contained emission lines that did not match any known element. They proposed a new element, which they called coronium. Later, it was realized that these lines came from highly ionized iron atoms stripped of many electrons, which only occurs at extremely high temperatures. Today, special instruments called coronagraphs can block the sun's bright disk, creating an artificial eclipse and allowing astronomers to study the corona at any time. Spacecraft like the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe have provided detailed images and data about the corona, revealing its complex structure and dynamics. But nothing quite matches the experience of seeing the corona with your own eyes during a total eclipse, a moment when the hidden atmosphere of the sun is briefly revealed. The sun influences Earth's climate. The sun is the primary driver of Earth's climate. Its energy warms the planet, evaporates water, drives winds, and powers ocean currents. Variations in the sun's output, even small ones, can influence Earth's climate over long timescales. During the sun's 11-year cycle, its total energy output varies by about 0.1%. While this may seem insignificant, it can have subtle effects on Earth's atmosphere and weather patterns, especially in the stratosphere. There have been periods in history when the sun's activity was unusually low. One notable example is the Maunder minimum, a period from about 1645 to 1715 when sunspots were extremely rare. This coincided with a period of cooler temperatures in Europe and North America, known as the Little Ice Age. Rivers froze that normally did not, and winters were harsher. While the exact relationship between the Maunder minimum and the Little Ice Age is still debated, it suggests that changes in solar activity can influence Earth's climate. On longer timescales, Earth's orbit and axial tilt change in predictable cycles, known as Milankovitch cycles. These cycles affect the distribution and intensity of sunlight reaching different parts of Earth, leading to ice ages and interglacial periods. The amount of solar energy Earth receives varies as the planet's orbit shifts from more circular to more elliptical, as the tilt of its axis changes and as the axis itself wobbles. These cycles operate over tens of thousands of years, shaping the long-term climate patterns of our planet. However, it is important to note that while the Sun influences climate, it is not the primary cause of the rapid climate change observed in recent decades. That is driven by human activities, particularly the emission of greenhouse gases. The Sun's output has remained relatively stable, even slightly decreasing in recent decades, while global temperatures have risen sharply. Understanding the Sun's role in climate helps scientists disentangle natural variations from human-caused changes, refining our understanding of Earth's complex climate system. The Sun produces sound waves that ripple through its interior. The Sun is not silent. Deep within its interior, convective currents and turbulent motions generate sound waves. These waves travel through the Sun's layers, bouncing and reflecting, creating a complex pattern of vibrations. The Sun essentially rings like a bell, oscillating with countless frequencies at once. These oscillations cause the Sun's surface to rise and fall by tiny amounts, just a few meters or so, over periods of about 5 minutes. Scientists study these oscillations through a field called Helioseismology, similar to how seismologists study earthquakes to learn about Earth's interior. By measuring the patterns of oscillations on the Sun's surface, researchers can infer what is happening deep inside, in regions that are otherwise impossible to observe directly. This has allowed them to measure the speed of sound at different depths, map the Sun's internal structure, and even detect large-scale flows and rotation patterns deep within. Helioseismology has confirmed many aspects of our theoretical models of the Sun. It has shown that the Sun's core rotates faster than its surface, revealed the thickness of the convective zone, and helped refine estimates of the Sun's age and composition. These sound waves are inaudible to us, of course. They are far too low in frequency and trapped within the Sun itself. But in a sense, the Sun hums with a complex symphony of vibrations, a song that reveals its inner workings to those who know how to listen. This technique has been so successful that astronomers now apply similar methods to other stars, a field called Astronomy. By studying the tiny oscillations of distant stars, they can learn about their interiors, just as we have done with the Sun. The Sun, once again, serves as our guide, a nearby laboratory where we can test techniques and ideas that we then apply to the wider universe. The Sun's equator rotates faster than its poles. Unlike a solid object like Earth, the Sun does not rotate as a single unit. Its equator completes a rotation in about 25 days, while regions near the poles take up to 35 days. This difference, called differential rotation, is a natural consequence of the Sun being made of plasma. There is no solid surface to enforce uniform rotation. Instead, different layers and latitudes can move independently, driven by convective currents and magnetic forces. This differential rotation has profound effects. It causes the Sun's magnetic field lines to stretch and twist. Imagine wrapping a rubber band around a ball and then rotating different parts of the ball at different speeds. The rubber band would wind tighter and tighter, becoming tangled and stressed. The same thing happens to the Sun's magnetic field. Over time, these twisted field lines rise to the surface, creating sunspots, active regions, and eventually, solar flares and coronal mass ejections. The twisting continues until the magnetic field becomes so complex that it reconfigures itself, a process that occurs roughly every 11 years. At that point, the magnetic poles flip and the cycle begins again. This 11-year solar cycle is a direct result of differential rotation and the dynamo process that generates the Sun's magnetic field. It is a beautiful example of how simple physical processes, when applied to a massive rotating sphere of plasma, can create complex and dynamic behavior. Differential rotation is not unique to the Sun. Many stars, especially younger, faster rotating ones, exhibit this behavior. Gas giant planets like Jupiter and Saturn also have differential rotation, with their equators spinning faster than their poles. It is a common feature of rotating fluids, whether they are stars, planets, or even Earth's atmosphere and oceans. The Sun, as always, is our example, the one place where we can observe these processes in detail and understand how they work. The Sun's gravity creates tides on Earth. Most people associate tides with the Moon, and indeed, the Moon is the primary cause of Earth's ocean tides. But the Sun also contributes. Though the Sun is much more massive than the Moon, it is also much farther away, and the strength of tidal forces decreases with distance. As a result, the Sun's tidal influence is about 46% that of the Moon's. When the Sun and Moon align, during a new moon or full moon, their tidal forces add together, creating higher high tides and lower low tides, known as spring tides. When they are at right angles, during the first and third quarter moons, their forces partially cancel out, creating smaller tides, called neap tides. Tides are caused by the differential gravitational pull across Earth. The side of Earth facing the Sun or Moon experiences a stronger pull than the center, and the center experiences a stronger pull than the far side. This creates a stretching effect, pulling the oceans into an elongated shape. Because Earth rotates beneath this bulge, we experience 2 high tides and 2 low tides each day. The Sun's contribution to this process is constant, but its alignment with the Moon varies, creating the fortnightly cycle of spring and neap tides. Tides are not just an oceanic phenomenon. The solid Earth also experiences tides, though they are much smaller, only a few centimeters. Even the atmosphere has tides, driven by both gravitational and thermal effects from the Sun. These atmospheric tides can influence weather patterns and the distribution of ozone in the stratosphere. The Sun's gravitational influence, though often overshadowed by the Moon's, is always present, shaping the rhythms of our planet. Throughout history, tides have been important for navigation, fishing, and coastal life. Mariners learned to time their voyages with the tides, using them to aid in entering and leaving harbors. In some places, tidal ranges can be extreme, with differences of over 50 feet between high and low tide. These tidal forces, driven by the gravitational interplay of Earth, Moon, and Sun, are reminders that we live in a dynamic system where celestial bodies interact and influence each other in subtle and profound ways. The Sun was worshipped as a deity across many cultures. To ancient peoples, the Sun was more than just a source of light and warmth. It was divine, a god or goddess deserving of reverence and worship. In ancient Egypt, the sun god Ra was one of the most important deities, often depicted as a man with the head of a falcon, crowned with a solar disk. Pharaohs were believed to be descended from Ra, and temples were built to honor him. The daily journey of the sun across the sky was seen as Ra, traveling in his solar barque, battling the forces of chaos and darkness each night. In ancient Greece, the sun was personified as Helios, who drove a chariot of fire across the sky each day. The Romans called him Sol. In Norse mythology, the sun was represented by the goddess Sol, who rode her chariot pursued by a wolf, Skoll, who would one day devour her during Ragnarok, the end of the world. In Hinduism, Surya is the sun god, depicted riding a chariot drawn by 7 horses, representing the 7 colors of sunlight. The Aztecs worshipped Tonatiuh, the sun god, and believed that he required nourishment in the form of human blood to continue his journey across the sky. This belief led to ritual sacrifices, a practice that horrified European conquistadors but was deeply tied to the Aztecs' cosmology. The Inca revered Inti, the sun god, and considered their emperor, the Sapa Inca, to be his earthly representative. They built magnificent temples, like Coricancha in Cusco, to honor him. Even in cultures without a single sun deity, the sun was central to religious and cosmological beliefs. In many indigenous American traditions, the sun was a powerful spirit or ancestor, a source of life and a symbol of renewal. Japanese mythology tells of Amaterasu, the sun goddess, who is considered the ancestral deity of the imperial family. The sun's importance transcends geography and time, reflecting humanity's universal dependence on its light and warmth. The sun's energy drives the water cycle. Every drop of rain, every river, every cloud owes its existence to the sun. The sun's energy evaporates water from oceans, lakes, and rivers, turning liquid water into water vapor that rises into the atmosphere. This process, driven by solar heating, is the beginning of the water cycle. As the water vapor rises, it cools and condenses into tiny droplets, forming clouds. These clouds drift with the wind, and when the droplets grow large enough, they fall as precipitation, rain, snow, sleet, or hail. This precipitation replenishes freshwater sources, feeding rivers and lakes, soaking into the ground to become groundwater and accumulating as ice in polar regions and mountain glaciers. Eventually, much of this water makes its way back to the oceans, where the cycle begins again. The sun's energy is the engine that drives this continuous movement of water, distributing it across the planet and making life possible. Without the sun, there would be no evaporation, no rain, no rivers. The water cycle would cease, and Earth would be a frozen, barren world. The water cycle also plays a crucial role in regulating Earth's climate. Water vapor is a greenhouse gas, trapping heat in the atmosphere and helping to keep the planet warm. Clouds reflect sunlight back into space, cooling the surface. The distribution of precipitation shapes ecosystems, creating deserts in some regions and rainforests in others. The sun's energy, through the water cycle, sculpts the face of the Earth, carving valleys, weathering mountains, and nourishing life in all its forms. Understanding the water cycle is essential for managing water resources, predicting weather, and addressing challenges like droughts and floods. As climate change alters temperature patterns and precipitation, the water cycle is affected, with some regions experiencing more intense storms and others facing prolonged droughts. The sun, as always, is at the center, its energy driving the processes that shape our world and sustain life. The sun appears to move across the sky, but it is Earth that rotates. To an observer on Earth, the sun appears to rise in the east, arc across the sky, and set in the west. This apparent motion has been observed since the dawn of humanity and was the basis for early models of the universe, where Earth was thought to be the center and the sun moved around it. This geocentric model, championed by ancient Greek astronomers like Ptolemy, held sway for over 1,000 years. It seemed to match what people observed. The sun moved, and the earth felt still. It was not until the 16th century that Nicolaus Copernicus proposed a heliocentric model, placing the sun at the center and Earth and the other planets in orbit around it. This was a radical idea, challenging not just scientific beliefs, but religious and philosophical ones as well. If Earth was not the center of the universe, what did that mean for humanity's place in creation? Copernicus's ideas were met with resistance, but they were eventually supported by observations, such as Galileo's discovery of moons orbiting Jupiter, proof that not everything revolved around Earth. We now know that the sun's apparent motion is an illusion created by Earth's rotation. Our planet spins on its axis once every 24 hours, and as it does, different parts of the surface face the sun. When your location rotates toward the sun, it appears to rise. When it rotates away, the sun seems to set. The sun itself is not moving across the sky. We are moving beneath it. This realization was one of the great shifts in human understanding, a moment when we recognized that our perception of motion is relative and that the universe does not revolve around us. Even today, we use language that reflects the old geocentric view. We say the sun rises and sets, even though we know it is Earth that moves. This is not inaccurate in a relative sense. From our frame of reference, the sun does move across the sky, but understanding the true cause, Earth's rotation, is a reminder of how science can reveal the underlying reality behind appearances, showing us that the universe is often more complex and wondrous than it first seems. The sun's energy powers the wind. When the sun heats the Earth's surface, it does so unevenly. The equator, where sunlight hits more directly, receives more energy than the poles, where sunlight arrives at an angle. This difference in heating creates temperature gradients, with warm air at the equator and cooler air near the poles. Warm air is less dense and rises, while cool air is denser and sinks. This creates a circulation pattern, with air flowing from high-pressure areas to low-pressure areas. But Earth's rotation complicates this simple pattern. As air moves from the equator toward the poles, the Coriolis effect, caused by Earth's spin, deflects it. In the northern hemisphere, moving air is deflected to the right. In the southern hemisphere, it is deflected to the left. This creates the prevailing wind patterns we observe, such as the trade winds near the equator and the westerlies in mid-latitudes. These wind patterns have shaped human history, guiding sailors across oceans and influencing the spread of cultures and trade. Local winds are also driven by solar heating. Sea breezes, for example, occur when the land heats up faster than the ocean during the day, causing air to rise over the land and cooler air from the sea to flow inland. At night, the process reverses, creating land breezes. Mountain and valley breezes follow similar patterns, driven by the sun's heating of slopes. Even large-scale phenomena like monsoons are fundamentally driven by seasonal changes in solar heating, which shift wind patterns and bring rains to certain regions. Wind is one of the most important ways the sun's energy is distributed across the planet. It mixes the atmosphere, transports moisture, and influences weather and climate. Wind has been harnessed by humans for thousands of years, from sailing ships to windmills to modern wind turbines generating electricity. In every gust of wind, every breeze, the sun's energy is at work, a reminder that the star at the center of our solar system is constantly shaping the world we live in. The sun creates shadows that tell time. Long before mechanical clocks, humans used the sun to measure time. The movement of shadows cast by objects provided a natural clock. The simplest device is a sundial, a flat surface with a raised pointer called a gnomon. As the sun moves across the sky, the shadow of the gnomon moves across the surface, marking the hours. Sundials have been used for thousands of years, found in ancient Egyptian, Babylonian, Greek, and Roman civilizations. Sundials are beautifully simple, requiring no power or mechanism, only the steady movement of the sun and Earth's rotation. However, they are not perfect timekeepers. Because Earth's orbit is slightly elliptical and its axis is tilted, the length of a solar day varies slightly throughout the year. This means a sundial can be off by as much as 16 minutes compared to a mechanical clock. This difference is known as the equation of time, and it has been understood since ancient times, though accurately calculating it required precise astronomical knowledge. In medieval and Renaissance Europe, sundials were common in town squares and on church buildings, allowing communities to coordinate activities. With the advent of mechanical clocks, sundials became less essential, but they remained popular as decorative and educational objects. Even today, sundials can be found in gardens, parks, and monuments, reminders of humanity's long relationship with the sun as a timekeeper. The concept of time zones also originated from the sun. Before the 19th century, each town kept its own local time based on the sun's position. Noon was when the sun reached its highest point in the sky. But with the advent of railroads and telegraphs, this became impractical. Standard time zones were established, dividing the world into regions where clocks are synchronized. Even so, the fundamental reference remains the sun. Coordinated universal time, the global time standard, is based on the solar time at the prime meridian. The sun has been a subject of art and poetry for millennia. The sun's beauty and power have inspired countless works of art and literature. In ancient cave paintings, sun symbols appear, suggesting that even our earliest ancestors were moved by the sun's presence. Ancient Egyptian art is filled with solar imagery, from the sun disk of Ra to the rays of the Aten, worshipped during the reign of Akhenaten. In medieval and Renaissance art, the sun often symbolized divine light, truth, and knowledge. Poets throughout history have written about the sun. Homer described it in the Iliad and the Odyssey. The Romantic poets, like William Wordsworth and Percy Bysshe Shelley, saw the sun as a symbol of nature's power and beauty. In his poem, To the Sun, Wordsworth marvels at the sun's ability to inspire awe and wonder. Emily Dickinson wrote of the sun as a playful, almost mischievous presence, while Walt Whitman celebrated it as a giver of life and energy. In visual art, the sun has been depicted in countless ways. Vincent van Gogh's paintings often feature vibrant suns, such as in The Sower and his famous Sunflower series. Claude Monet painted the sun rising over water in Impression Sunrise, a work that gave the Impressionist movement its name. In Japanese art, the rising sun is a central motif, symbolizing new beginnings and national identity. The sun appears in the works of artists from every culture, each bringing their own perspective and interpretation. Modern art continues this tradition. The sun appears in abstract paintings, sculptures, and installations, often exploring themes of energy, light, and life. Photography has allowed artists to capture the sun in new ways, from stunning sunsets to solar eclipses to the play of light and shadow. The sun remains an enduring subject, a source of inspiration that transcends time and culture, reminding us of its central place in human experience. The sun's light is essential for vitamin D production. Sunlight is not just a source of warmth and light. It is also essential for our health. When ultraviolet B, UVB, rays from the sun strike our skin, they trigger a chemical reaction that produces vitamin D. This vitamin is crucial for many bodily functions, including bone health, immune system function, and mood regulation. Without adequate vitamin D, bones can become weak and brittle, a condition known as rickets in children and osteomalacia in adults. For most of human history, people spent significant time outdoors, and vitamin D deficiency was rare. But in modern times, with many people working indoors and spending less time in the sun, deficiency has become more common. Factors such as geographic location, skin pigmentation, and the use of sunscreen also affect vitamin D production. People living far from the equator, where sunlight is less intense, especially in winter, are at higher risk of deficiency. Vitamin D can also be obtained from certain foods, such as fatty fish, fortified milk, and egg yolks, and from supplements. But sunlight remains the most natural and effective source. Just 10 to 30 minutes of midday sun exposure, several times a week, is usually sufficient for most people. Though this varies depending on skin type and location, it is a reminder that we have evolved in a relationship with the sun, and our bodies are adapted to use its light in ways that go beyond vision. However, too much sun exposure can be harmful, increasing the risk of skin cancer and premature aging. Finding a balance is important. Getting enough sun for vitamin D production while protecting the skin from excessive UV radiation. Sunscreen, protective clothing, and avoiding the midday sun can help manage this balance. The sun gives, but it also requires respect and caution. Like many things in nature, it offers benefits and risks, and understanding both is key to living well. Solar observatories study the sun constantly. To understand the sun, scientists have built observatories dedicated to studying it. Some are on the ground, placed in locations with clear skies and minimal atmospheric distortion. Others are in space, above Earth's atmosphere, where they can observe the sun at wavelengths that do not reach the surface, such as ultraviolet, X-rays, and extreme ultraviolet light. These observatories monitor the sun continuously, tracking sunspots, flares, coronal mass ejections, and other phenomena. One of the most important ground-based observatories is the National Solar Observatory in the United States, which operates facilities in multiple locations. The Atacama Desert in Chile, one of the driest places on Earth, is home to several solar telescopes, taking advantage of the clear, stable atmosphere. In space, missions like the Solar and Heliospheric Observatory, SOHO, have been observing the sun for over 25 years, providing an uninterrupted view and a wealth of data. More recent missions have brought us even closer to the sun. The Parker Solar Probe, launched in 2018, is designed to fly through the sun's corona, closer than any spacecraft has ever ventured. It is equipped with instruments to measure magnetic fields, plasma, and energetic particles, protected by a heat shield that can withstand temperatures over 1,400 degrees Celsius. The probe has already made several close approaches, or perihelia, and will continue to spiral closer, eventually coming within about 4 million miles of the sun's surface. The Solar Dynamics Observatory, SDO, launched in 2010, provides high-resolution images of the sun in multiple wavelengths, allowing scientists to watch the sun's atmosphere in incredible detail. It captures images every few seconds, creating movies that show the dynamic behaviour of solar flares, prominences, and the constant churning of the photosphere. These observations have revolutionized our understanding of the sun, revealing processes that were previously only theoretical. Studying the sun is not just about satisfying curiosity. It has practical implications. Understanding solar activity helps us predict space weather, which can affect satellites, astronauts, power grids, and communication systems. As our technology becomes more advanced and more dependent on space-based infrastructure, the importance of solar research grows. The Sun, once a distant mystery, is now a subject of intense study, its secrets gradually being revealed by human ingenuity and determination. The Sun will eventually become a white dwarf. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. When that happens, it will begin fusing hydrogen in a shell around the core, and the core itself will contract and heat up. This will cause the Sun's outer layers to expand dramatically, and it will become a red giant. During this phase, the Sun may grow large enough to engulf Mercury and Venus, and possibly even Earth. Life on Earth, if it still exists, will certainly not survive this transformation. As a red giant, the Sun will begin fusing helium into carbon and oxygen in its core. This phase will last a few 100 million years, much shorter than its time on the main sequence. The Sun will pulsate, shedding its outer layers in waves, creating a planetary nebula, a beautiful shell of glowing gas expanding into space. At the center of this nebula will be the Sun's core, now exposed, a small, incredibly dense object about the size of Earth, but containing a significant fraction of the Sun's original mass. This core is a white dwarf, the remnant of a star that has exhausted its nuclear fuel. It will no longer generate energy through fusion. Instead, it will shine simply from the residual heat left over from its earlier life. Over billions of years, the white dwarf will slowly cool, fading from white to yellow to red, and eventually becoming a cold, dark cinder called a black dwarf. However, the universe is not old enough for any black dwarfs to exist yet. Even the oldest white dwarfs are still glowing faintly. The Sun's transformation into a white dwarf is its ultimate fate, the end of its life as a star. But in a sense, it is not a true ending. The elements forged in the Sun's core, the carbon and oxygen, will be released into space as part of the planetary nebula. These elements may one day be incorporated into new stars, new planets, and perhaps new forms of life. The Sun, like all stars, is part of a cosmic cycle, a process of birth, life, death, and rebirth that has been ongoing for billions of years and will continue for billions more. The Sun is one of billions of stars in the Milky Way. The Sun is special to us, but in the grand scheme of the universe, it is ordinary. It is one of an estimated 200 to 400 billion stars in the Milky Way galaxy. Many of these stars are similar to the Sun, medium-sized, yellow stars in their main sequence phase. Others are much larger, blue giants and supergiants, blazing brightly but living fast and dying young. Still others are smaller, red dwarfs, dim and cool, but incredibly long-lived, with lifespans that could exceed the current age of the universe. The Milky Way itself is just one of billions, perhaps trillions, of galaxies in the observable universe. Each galaxy contains its own population of stars, many with their own planetary systems. The universe is filled with suns, countless stars shining across the cosmos, each one a potential source of light and warmth for worlds we will never see. The realization of this vastness is both humbling and awe-inspiring. We are part of something unimaginably large, a universe filled with stars and worlds beyond counting. Yet, the Sun remains unique to us. It is our star, the one that gave birth to our solar system, the one that nurtured life on Earth, the one that will continue to shine for billions of years, watching over our world. To the countless other worlds that may exist around other stars, their suns are just as unique, just as important. Each star is the center of its own story, the heart of its own system. In this sense, every star is special, even if the universe is full of them. The sun connects us to the cosmos. When we look at other stars, we are looking at distant suns, each one a reminder that we are part of a larger whole. The atoms in our bodies were forged in stars. The energy that powers our civilization comes from a star, and our understanding of the universe has grown by studying our star. The sun is both ordinary and extraordinary, a single star among billions, and the most important star there is. The sun's light takes 8 minutes to reach Earth. This fact is worth repeating, for it is both simple and profound. The sun is 93 million miles away, and light travels at 186,000 miles per second. At that speed, it takes light about 8 minutes and 20 seconds to cross the distance from the sun to Earth. This means that the sunlight you see right now left the sun over 8 minutes ago. You are not seeing the sun as it is in this moment, but as it was 8 minutes in the past. If something were to happen to the sun, we would not know immediately. We would continue to see it shining, feel its warmth, and experience daylight for more than 8 minutes after the event. Only then would the change reach us. This is true for all objects in space. We see them not as they are now, but as they were when the light we are receiving left them. The farther away something is, the further back in time we are looking. This time delay also affects space exploration. Commands sent to spacecraft near other planets take minutes or even hours to arrive, depending on the distance. When engineers control a Mars rover, they must plan their commands carefully, knowing that the signal will take anywhere from 4 to 24 minutes to reach Mars, depending on the planet's positions in their orbits. Real-time control is impossible. Instead, spacecraft must be semi-autonomous, able to make decisions on their own. The 8-minute delay between the Sun and Earth is a constant reminder of the distances involved in space. Even our closest neighbor is far enough away that light, the fastest thing in the universe, takes noticeable time to reach us. As we look outward to other stars and galaxies, this delay grows, and we peer deeper into the past. The universe is not just vast in space, but also in time, and light is the messenger that brings us information from across the cosmos. Solar eclipses have been recorded throughout history. Humans have been recording solar eclipses for thousands of years. Ancient Chinese astronomers kept detailed records, some dating back over 4,000 years. These records were important for calendrical and astrological purposes, and eclipses were often interpreted as omens. In ancient Babylon, astronomers tracked eclipses as part of their efforts to understand the heavens and predict future events. Their observations, recorded on clay tablets, are among the earliest astronomical records we have. In ancient Greece, the philosopher Thales is said to have predicted an eclipse in 585 before Common Era. Whether he truly predicted it or simply made an educated guess based on patterns is uncertain, but the story reflects the importance placed on understanding these events. The Greek historian Herodotus wrote about an eclipse that occurred during a battle between the Medes and the Lydians, which supposedly caused both sides to stop fighting and make peace, awed by the sudden darkness. In medieval Europe, eclipses were recorded by monks and chroniclers, often with descriptions of fear and wonder. One of the most famous historical eclipses occurred in 1133, described as a time when the sun was darkened and people feared the end of the world. In the Americas, Mayan and Aztec astronomers also recorded eclipses, incorporating them into their complex calendars and cosmologies. Eclipses were seen as moments when the natural order was disrupted, requiring rituals and ceremonies to restore balance. These historical records are valuable to modern astronomers. By comparing ancient descriptions of eclipses with modern calculations, scientists can refine their understanding of Earth's rotation and the Moon's orbit, both of which change very slowly over time. Ancient eclipses serve as fixed points in time, allowing researchers to measure how the Earth-Moon system has evolved. History and astronomy intersect, showing how observations made thousands of years ago still contribute to our understanding today. The Sun's activity affects radio communications on Earth. When the Sun erupts with a solar flare or coronal mass ejection, it sends bursts of radiation and charged particles streaming toward Earth. These events can disrupt radio communications, especially at certain frequencies. High frequency, HF, radio waves, used for long-distance communication, reflect off the ionosphere, a layer of Earth's atmosphere ionized by solar radiation. During a solar flare, increased ionization can cause these waves to be absorbed rather than reflected, leading to radio blackouts. These blackouts can last for minutes to hours, affecting aviation, maritime, and military communications. Pilots flying over polar regions, where radio communication depends on HF signals, are especially vulnerable. During major solar storms, airlines may reroute flights to avoid these areas, adding time and cost to journeys. Similarly, ships at sea that rely on HF radio for communication can find themselves temporarily cut off. On the other hand, solar activity can sometimes enhance radio communication at lower frequencies. Auroras, caused by charged particles interacting with Earth's magnetic field, can reflect radio waves, allowing operators to make unusual long-distance contacts. Amateur radio enthusiasts often monitor space weather, taking advantage of these conditions to communicate with distant stations. The Sun's influence on radio communication is a reminder of how deeply connected we are to our star, even in our technological systems. With the increasing importance of satellite communications, understanding and predicting solar activity has become even more critical. Satellites can be damaged or disrupted by solar storms, affecting GPS, television broadcasts, and internet services. Space agencies and private companies monitor the Sun constantly, using observations from spacecraft and ground-based observatories to forecast space weather and protect infrastructure. The Sun's activity is not just a scientific curiosity. It has real-world impacts on our daily lives. The Sun has inspired scientific discoveries for centuries. The Sun has been at the center of many important scientific breakthroughs. Galileo's observations of sunspots helped establish that the heavens were not perfect and unchanging, challenging long-held beliefs. Isaac Newton used observations of sunlight passing through a prism to demonstrate that white light is composed of many colors, laying the foundation for the field of optics. His work showed that light could be studied scientifically, leading to deeper understanding of its nature. In the 19th century, scientists studying the Sun's spectrum noticed dark lines, gaps in the rainbow of colors. These lines, called Fraunhofer lines, after the scientist who mapped them, were eventually understood to be caused by absorption of light by elements in the Sun's atmosphere. Each element absorbs light at specific wavelengths, creating a unique pattern of lines. This discovery gave birth to spectroscopy, a technique that allows scientists to determine the composition of stars and other celestial objects without ever physically touching them. Spectroscopy led to the discovery of helium, an element first identified in the Sun before it was found on Earth. The name helium comes from Helios, the Greek sun god. This was the first time an element was discovered outside Earth, a testament to the power of spectroscopy and the importance of studying the Sun. Since then, spectroscopy has become one of the most important tools in astronomy, chemistry, and physics. In the 20th century, the Sun helped confirm Einstein's theory of general relativity, During a total solar eclipse in 1919, astronomers measured the positions of stars near the Sun and found that their light was bent by the Sun's gravity, exactly as Einstein's theory predicted. This observation made Einstein famous overnight and solidified general relativity as one of the pillars of modern physics. The Sun, once again, served as a laboratory, allowing scientists to test and validate fundamental theories about the universe. The Sun's atmosphere extends far beyond what we can see. The Sun does not have a sharp boundary. Its atmosphere gradually thins as it extends into space, eventually merging with the solar wind and filling the heliosphere. The visible surface, the photosphere, is just the beginning. Above it lies the chromosphere, and above that, the corona, which stretches millions of miles outward. But even the corona does not mark the end of the Sun's influence. The solar wind carries the Sun's magnetic field and particles throughout the solar system and beyond. The heliosphere, the bubble of space dominated by the Sun's influence, extends far beyond the planets. Its boundary, the heliopause, is where the solar wind meets the interstellar medium, the thin gas that fills the space between stars. The Voyager 1 and Voyager 2 spacecraft, launched in the 1970s, have crossed this boundary, entering interstellar space. Yet, even there, they still feel the Sun's gravity, and they will for many years to come. The Sun's reach is immense, shaping the space around it for billions of miles. Within the heliosphere, the Sun's magnetic field is carried outward by the solar wind, creating a complex structure with sectors of different polarity. These magnetic fields interact with the magnetic fields of planets, moons, and other objects, shaping their environments. Earth's magnetosphere, for example, is constantly buffeted by the solar wind, compressing on the side facing the Sun and stretching into a long tail on the opposite side. This interaction protects us from much of the solar wind's harmful radiation, but it also creates beautiful auroras. The Sun's atmosphere, in a sense, envelops the entire solar system. We live within it, bathed in its light, and shielded by our planet's magnetic field. Every object in the solar system, from the smallest asteroid to the largest planet, exists within the Sun's extended atmosphere. It is a reminder that the Sun is not just a distant object, but the environment we inhabit, the space we call home. The Sun's magnetic field flips every 11 years. The Sun's magnetic field is not static. It changes over time, driven by the motion of plasma in the Sun's interior. As the Sun rotates, with its equator spinning faster than its poles, the magnetic field lines become twisted and tangled. Over the course of about 11 years, this twisting reaches a peak, and the magnetic field becomes so complex that it reconfigures itself. When this happens, the north and south magnetic poles flip, a process that occurs smoothly over a period of months. This cycle is known as the solar cycle, and it has been observed for centuries. At the beginning of the cycle, the Sun is relatively quiet, with few sunspots. As the cycle progresses, magnetic activity increases. More sunspots appear, along with solar flares and coronal mass ejections. At solar maximum, the Sun is covered with active regions, and space weather is at its most intense. Then, as the cycle wanes, activity decreases, and the Sun enters solar minimum once again, calm and relatively spotless. The solar cycle is not perfectly regular. Some cycles are stronger than others, with more sunspots and greater activity. The cycle that peaked in 1958, for example, was one of the strongest on record, with intense auroras visible far from the poles and disruptions to radio communications and power grids. Other cycles are weaker, with fewer sunspots and less activity. Scientists are still working to understand what causes these variations and how to predict future cycles. The magnetic flip does not happen all at once. During the transition, the Sun's magnetic field is highly complex, with multiple poles and twisted field lines. Eventually, the field settles into a simpler configuration, with the poles reversed. The process then begins again, and over the next 11 years, the field will flip back. This cycle has been ongoing for as long as the Sun has existed, a rhythmic pulse driven by the dynamo deep within. The Sun is the source of almost all energy on Earth. Nearly every form of energy we use can be traced back to the Sun. Fossil fuels, coal, oil, and natural gas are the remains of ancient plants and organisms that captured sunlight through photosynthesis millions of years ago. When we burn these fuels, we are releasing energy that was originally sunlight, stored in chemical form. Wind energy comes from the Sun's uneven heating of Earth's surface, which drives atmospheric circulation. Hydroelectric power depends on the water cycle, which is powered by solar heating. Even the food we eat is solar energy, converted by plants into sugars and starches. When we eat plants, or animals that ate plants, we are consuming that stored solar energy and using it to power our bodies. In a very real sense, we are solar-powered, as is almost all life on Earth. The few exceptions are organisms that rely on geothermal energy or chemical energy from Earth's interior. But these are rare compared to the vast majority of life that depends on photosynthesis. Renewable energy technologies directly harness the Sun's power. Solar panels convert sunlight into electricity, providing a clean and sustainable energy source. As technology improves, solar power is becoming more efficient and affordable, playing an increasingly important role in the global energy mix. Wind turbines, another form of renewable energy, are also ultimately powered by the Sun, capturing the kinetic energy of air currents driven by solar heating. The Sun has been powering Earth for billions of years, and it will continue to do so for billions more. It is the most abundant and reliable energy source we have, shining down every day, free and inexhaustible. As humanity seeks to transition away from fossil fuels and reduce our impact on the environment, the Sun offers a path forward, a source of energy that is clean, renewable, and capable of meeting our needs. The Sun has always been our benefactor, and it will continue to be, if we learn to harness its gifts wisely. The Sun's outer layers will one day drift away. When the Sun becomes a red giant, it will not remain stable. Its outer layers will become tenuous, weakly bound by gravity. Stellar winds, streams of gas escaping from the surface, will intensify, carrying away mass. Over time, the Sun will shed its outer envelope in a series of pulses, each one ejecting gas and dust into space. These ejected layers will form a glowing shell around the Sun, lit by the ultraviolet radiation from the hot core. This structure is called a planetary nebula, though it has nothing to do with planets. Planetary nebulae are some of the most beautiful objects in astronomy. They come in a variety of shapes, from spherical shells to intricate hourglass and butterfly forms, sculpted by magnetic fields, rotation, and the interaction of different layers of gas moving at different speeds. They glow with vibrant colors, reds from hydrogen, blues and greens from oxygen, each hue revealing the elements present and the temperature of the gas. Through telescopes, they appear delicate and ephemeral, like cosmic flowers blooming in the darkness. The planetary nebula phase lasts only a few tens of thousands of years, a brief moment in the life of a star. The gas continues to expand, eventually dispersing into the interstellar medium, mixing with other clouds of gas and dust. This material, enriched with the elements forged in the Sun's core, will one day become part of new stars, new planets, and perhaps new life. The Sun's outer layers, once part of our star, will be recycled, contributing to the ongoing cycle of stellar birth and death. At the center of the planetary nebula will be the Sun's core, now a white dwarf. It will be incredibly hot, tens of thousands of degrees Celsius, glowing with the residual heat of its former nuclear fires. But it will no longer generate energy through fusion. It will simply cool, slowly fading over billions of years. The white dwarf will be about the size of Earth, but incredibly dense, with a teaspoon of its material weighing as much as a car. It is the final resting state of a star like the Sun, a quiet ending after billions of years of shining. The Sun is approaching the galactic plane. The Sun, along with the rest of the solar system, is not stationary. It orbits the center of the Milky Way galaxy, traveling at a speed of about 500 kilometers per second. It takes roughly 230 million years to complete one orbit, a period sometimes called a galactic year. Over the course of this orbit, the Sun moves up and down relative to the galactic plane, the flat disk where most of the galaxy's stars are concentrated. Currently, the Sun is slightly above the galactic plane and moving downward toward it. In a few million years, it will cross the plane and continue to the other side before eventually returning. This oscillation takes about 33 million years to complete one full cycle, up and down. As the Sun moves through different regions of the galaxy, it encounters different environments, varying densities of gas and dust, and different levels of cosmic radiation. Some scientists have speculated that the Sun's passage through the galactic plane could have effects on Earth, such as increased meteor impacts or changes in cosmic ray exposure, which might influence climate or even mass extinctions. However, these ideas are controversial and not widely accepted. The evidence for such effects is weak, and the mechanisms are unclear. The Sun's motion through the galaxy is a reminder that the solar system is not isolated, but part of a larger, dynamic structure. As the Sun orbits the galaxy, it also moves relative to nearby stars. Over time, the constellations we see in the night sky will change as stars drift apart. In a few 100,000 years, the familiar patterns we know will be unrecognizable. The Sun's journey through the galaxy is a slow, majestic voyage, carrying Earth and the other planets along, a cosmic caravan traveling through the Milky Way. The Sun's light supports complex ecosystems, from the tiniest plankton in the ocean to the largest trees in the rainforest. Life on Earth thrives because of the Sun. Ecosystems are intricate networks of organisms interacting with each other and their environment. And at the base of almost every ecosystem is photosynthesis. Plants and algae capture sunlight and use it to produce energy, which then flows through food chains. Herbivores eat the plants, carnivores eat the herbivores, and decomposers break down dead material, returning nutrients to the soil. In the ocean, phytoplankton, microscopic organisms that photosynthesize, form the base of the marine food web. They are eaten by zooplankton, which are in turn eaten by small fish, which are eaten by larger fish, and so on up the chain to apex predators like sharks and whales. Phytoplankton also produce much of the oxygen we breathe, estimated at around 50% of Earth's oxygen. They are tiny, often invisible to the naked eye, but their collective impact is immense, shaping the chemistry of the ocean and the atmosphere. On land, forests, grasslands, and other ecosystems follow similar patterns. The Sun's energy is captured by plants, which support vast communities of animals, fungi, and microorganisms. Even in deserts, Where water is scarce, life persists, adapted to make the most of the sun's energy. Cacti and other desert plants have evolved strategies to conserve water while still photosynthesizing, supporting insects, reptiles, and mammals that have adapted to the harsh conditions. Ecosystems are resilient, but they depend on the sun's steady light. Changes in solar energy, whether from natural variations or human-caused factors like deforestation and pollution, can disrupt these systems. Understanding the connection between the sun and life on Earth is crucial for conservation and sustainability. The sun provides, but it is up to us to ensure that the ecosystems that depend on it are protected and preserved for future generations. The sun's fusion process is incredibly efficient. Nuclear fusion is the most efficient energy source known. In the sun's core, 4 hydrogen nuclei fuse to form one helium nucleus. The mass of the helium nucleus is slightly less than the combined mass of the 4 hydrogen nuclei. This missing mass, about 0.7% of the original mass, is converted into energy according to Einstein's equation, E equals mc squared. This may seem like a small amount, but because the speed of light squared is such a large number, even a tiny amount of mass yields enormous energy. To put this in perspective, if we could harness fusion on Earth in the same way the sun does, a few grams of hydrogen could provide enough energy to power a city for a day. The sun converts about 600 million tons of hydrogen into helium every second, releasing energy equivalent to billions of nuclear bombs. Yet, it does so steadily and continuously, a controlled fusion reaction that has been ongoing for billions of years and will continue for billions more. Scientists have been working for decades to achieve controlled nuclear fusion on Earth. The goal is to replicate the sun's energy source, creating a nearly limitless supply of clean energy. Fusion produces no greenhouse gases, no long-lived radioactive waste, and uses fuels that are abundant, such as hydrogen isotopes found in seawater. However, achieving the conditions necessary for fusion, temperatures of millions of degrees and immense pressure, is incredibly challenging. Progress is being made. Experimental reactors like ITER, currently under construction in France, aim to demonstrate that fusion can produce more energy than it consumes, a key milestone. If successful, fusion could revolutionize energy production, providing power for generations without the environmental costs of fossil fuels. The sun has been showing us the way for billions of years, and now we are learning to follow its example. The sun has different rotation periods at different latitudes. As mentioned earlier, the sun's equator rotates faster than its poles, but this is worth exploring in more depth. The equatorial region completes a rotation in about 25 days, while regions at 30 degrees latitude take about 26 days, and the poles take around 35 days. This differential rotation is measured by tracking sunspots and other features as they move across the sun's surface. This variation in rotation speed has profound effects on the sun's magnetic field. As different parts of the sun rotate at different rates, magnetic field lines get stretched and wound up, like twisting a rope. This creates magnetic energy that builds up over time. Eventually, this energy is released in the form of solar flares, coronal mass ejections, and the formation of sunspots. The 11-year solar cycle is driven by this process, with the magnetic field building up, reaching a maximum, and then reconfiguring. Differential rotation is common among stars, especially those with deep convective zones like the sun. It is a natural consequence of being made of fluid rather than solid material. In the sun's interior, convective currents transport heat from the core to the surface, and these currents, combined with rotation, create the complex motions that generate the sun's magnetic field. This process, called the solar dynamo, is similar to how Earth's liquid iron core generates its magnetic field. Understanding the Sun's differential rotation helps scientists model other stars. By studying the Sun in detail, we can infer what is happening in stars that are too distant to observe directly. The Sun, once again, serves as a laboratory, a nearby example where we can measure, test, and learn, applying those lessons to the broader universe. Differential rotation is just one of many phenomena that connect the Sun to the wider cosmos, showing that the processes happening in our star are universal. The Sun's surface is covered in granules. If you could zoom in on the Sun's photosphere, you would see a textured surface, covered in bright cells, surrounded by darker lanes. These are granules, convection cells, where hot plasma rises from below, cools, and sinks back down. Each granule is enormous, typically about 1,000 kilometers across, roughly the size of Texas. Yet, despite their size, they are short-lived, lasting only about 10 to 20 minutes before dissipating and being replaced by new ones. The pattern of granules gives the photosphere a mottled appearance, like the surface of boiling water. This is an apt comparison, as the process is similar. Hot plasma rises in the center of each granule, spreading outward when it reaches the surface. As it cools, it becomes denser and sinks back down at the edges, creating the darker lanes. This convective motion is how the Sun transports heat from its interior to the surface, carrying energy that will eventually be radiated into space as light. Watching the granules change and evolve is mesmerizing. Time-lapse videos from solar observatories show the photosphere in constant motion, with granules appearing, growing, shrinking, and disappearing in an endless dance. It is a reminder that the Sun is not a static object, but a dynamic, living star, constantly churning and evolving. Every point of light we see is part of this process, energy rising from the depths, cooling and sinking, over and over. In addition to granules, the Sun's surface also shows larger structures called supergranules, which are about 30,000 kilometers across and last about a day. These are convection cells on a larger scale, driven by the same basic process, but involving deeper layers of the Sun's convective zone. Supergranules are harder to see than granules, requiring sensitive instruments and careful analysis. They are part of the complex flow patterns that shape the Sun's surface and transport energy and magnetic fields. The Sun's energy output is remarkably constant. Despite the Sun's dynamic activity, its total energy output, or luminosity, is remarkably stable. It varies by only about 0.1% over the 11-year solar cycle. This stability is crucial for life on Earth. If the Sun's output varied significantly, Earth's climate would be chaotic, making it difficult for life to adapt and thrive. The Sun has been shining with roughly the same brightness for billions of years, providing the steady energy needed for life to evolve and flourish. However, on much longer timescales, the Sun's luminosity does change. When the Sun first formed, it was about 30% less bright than it is today. Over billions of years, as helium accumulates in the core from fusion, the core becomes denser and hotter, causing the Sun to gradually brighten. This process is slow, occurring over hundreds of millions to billions of years, but it has significant implications for Earth's long-term climate. The fact that Earth has remained habitable despite the Sun's increasing brightness is known as the faint young sun paradox. Geological evidence shows that liquid water has existed on Earth's surface for most of its history, yet the early Sun was much dimmer. The solution likely involves greenhouse gases, which trapped heat and kept Earth warm enough for liquid water. As the sun brightened, these gases decreased, maintaining a relatively stable temperature. In the future, as the sun continues to brighten, Earth will eventually become too hot for liquid water to exist on the surface. This may happen in about 1 billion years, long before the sun becomes a red giant. Life, as we know it, will no longer be possible, and Earth will become a barren, lifeless world. But for now, we live in a time of balance. The sun is a sacred being, a source of life, and a teacher of important lessons. The sun's journey across the sky mirrors the journey of life, from birth to death and, in many beliefs, to rebirth. The winter solstice, the shortest day of the year, has been celebrated for millennia as a turning point. After the solstice, the days begin to lengthen, and the sun's power returns. This has been seen as a time of renewal and hope, a reminder that even in the darkest times, light will return. Festivals like Yule, Saturnalia, and Christmas are held around the winter solstice, celebrating the return of the sun and the promise of spring. These traditions, rooted in ancient agricultural societies, continue to resonate today. The sun's symbolism extends beyond religion and spirituality. In literature, art, and everyday language, the sun represents warmth, happiness, and positivity. A sunny day lifts spirits, while a cloudy day can feel gloomy. We speak of someone having a sunny disposition, meaning they are cheerful and optimistic. The sun is woven into the fabric of human culture, a universal symbol that transcends time and place, reminding us of the light that sustains us, both physically and spiritually. The sun will outlive all rocky planets. When the sun expands into a red giant, its outer layers will reach far into the solar system. Mercury, the closest planet, will almost certainly be consumed. Venus, too, is likely to be engulfed. Earth's fate is less certain. Some models suggest the sun will expand far enough to swallow Earth, while others predict Earth will survive, though barely, left as a scorched, lifeless rock orbiting a dying star dwarf. The warmth will fade, and the outer solar system will freeze once more. The planets will continue to orbit, now circling a faint, cooling ember. The solar system will become a cold, dark place, a graveyard of worlds orbiting a dead star. This is the fate awaiting our sun and its family of planets, a reminder that even the most enduring structures in the universe are temporary. Yet, this ending is also a beginning. The material shed by the sun will enrich the interstellar medium, contributing to the birth of new stars and planets. The atoms that once made up the sun and the Earth, and even us, will be recycled, becoming part of future generations of stars and worlds. In the cosmic cycle, nothing is truly lost. Everything is transformed, endlessly reborn in new forms. The sun's death will seed the creation of new life elsewhere, continuing the ancient dance of birth, death, and rebirth that has shaped the universe for billions of years. The sun's light travels through space, unimpeded. Light from the sun travels through the vacuum of space without interference. There is no air, no dust, no obstacles to slow it down or scatter it, at least not significantly. This is why sunlight in space is harsh and direct, unlike the softer, diffused light we experience on Earth. Astronauts aboard the International Space Station see the sun as an intensely bright point of light, so bright that looking at it directly, even for a moment, can cause serious eye damage. On Earth, the atmosphere scatters sunlight, creating the blue sky and the softer, ambient light we experience. But in space, there is no atmosphere, and the background is pitch black. When the sun is in view, everything is brilliantly lit. When it is not, panels can capture the sun's energy directly, without atmospheric losses. providing a reliable source of power. Many spacecraft, from satellites in Earth orbit to the Mars rovers, rely on solar energy. As humanity ventures farther into the solar system, the Sun will remain our most important source of energy, shining across the void, undiminished and ever-present. The Sun's neutrinos pass through everything. Neutrinos are among the strangest particles in nature. They are produced in enormous numbers by the nuclear fusion reactions in the Sun's core. Every second, trillions upon trillions of neutrinos stream out from the Sun, traveling at nearly the speed of light. Unlike photons, which interact with matter and can be absorbed or scattered, neutrinos barely interact with anything. They pass through the Sun, through the Earth, and through you as if nothing is there. Detecting neutrinos is incredibly difficult because of this lack of interaction. To catch even a few, scientists build large detectors, often placed deep underground, to shield them from other particles. One famous detector is the Sudbury Neutrino Observatory in Canada, located in a mine more than 2 kilometers underground. It uses a large tank of heavy water to detect the faint flashes of light produced when a neutrino occasionally interacts with a particle in the water. Despite the trillions of neutrinos passing through the detector every second, only a handful are detected each day. The study of solar neutrinos has confirmed our understanding of how the Sun produces energy. Early neutrino experiments detected fewer neutrinos than expected, a puzzle known as the solar neutrino problem. This discrepancy was eventually explained by the discovery that neutrinos can change type, or flavor, as they travel, a phenomenon called neutrino oscillation. Some of the neutrinos produced in the Sun change into types that the early detectors could not see. This discovery was a major breakthrough in particle physics and earned the Nobel Prize. Neutrinos are messengers from the Sun's core, the only particles that can escape immediately and carry direct information about the fusion reactions happening deep inside. By studying them, scientists can peer into the heart of the Sun, seeing processes that are otherwise hidden. Neutrinos remind us that the universe is filled with invisible phenomena, particles and forces that shape reality but go unnoticed by our senses. The Sun produces them by the trillions every second, and they pass through us, silent and unseen, a constant reminder of the hidden workings of nature. The Sun's light inspired early navigation. Long before GPS and modern navigation tools, sailors relied on the Sun to find their way across the oceans. By measuring the Sun's angle above the horizon at noon, when it reaches its highest point, navigators could determine their latitude, their position north or south of the equator. This technique, combined with knowledge of the date, allowed sailors to know how far north or south they had traveled. Instruments like the sextant and astrolabe were developed to make these measurements more accurate. Determining longitude, one's position east or west, was more challenging. It required knowing the exact time, which was difficult on a moving ship. The solution came in the 18th century with the invention of the marine chronometer, a highly accurate clock that could keep time at sea. By comparing the local time, determined by the Sun's position, with the time at a reference location, navigators could calculate their longitude. This breakthrough revolutionized navigation, allowing sailors to cross oceans with confidence and opening the age of global exploration. The Sun also guided travelers on land. In the northern hemisphere, the Sun is due south at noon, providing a natural compass. By observing the Sun's movement across the sky, travelers could orient themselves and maintain their direction. Indigenous peoples around the world developed sophisticated navigation techniques based on the Sun, stars, and natural landmarks. These skills, passed down through generations, allowed them to traverse vast distances, from the Pacific Islanders, who crossed oceans in canoes, to the nomadic peoples who navigated deserts and steppes. Today, we have satellites and digital maps, but the fundamental principles of solar navigation remain. The sun still rises in the east and sets in the west, providing a reliable reference for direction. In survival situations, when technology fails, knowledge of solar navigation can be life-saving. The sun, as it has for thousands of years, continues to guide those who know how to read its movements. The sun's diameter is over 100 times Earth's. The sun is enormous. Its diameter is about 1.4 million kilometers, roughly 109 times the diameter of Earth. To put this in perspective, if the sun were a hollow sphere, you could fit about 1.3 million Earths inside it. The sheer scale is difficult to grasp. We see the sun as a disk in the sky, but that disk is a sphere large enough to contain our entire planet millions of times over. Despite its size, the sun is not particularly large compared to other stars. It is classified as a medium-sized star, or more specifically, a G-type main sequence star, often called a yellow dwarf. There are stars much larger than the sun. Red supergiants like Betelgeuse and UY Scuti have diameters hundreds of times larger than the sun's. If Betelgeuse were placed at the center of our solar system, its surface would extend beyond the orbit of Mars. Such stars are rare, but they show that the sun, while huge to us, is modest in the grand scheme of the universe. There are also stars much smaller than the sun. Red dwarfs, the most common type of star, have diameters only about 10 to 40% that of the sun. They are cooler, dimmer, and much longer lived, burning their fuel so slowly that some may shine for trillions of years. The sun sits comfortably in the middle, large enough to fuse hydrogen efficiently, but not so large that it burns out quickly. This balance is part of what makes the sun a good host star for life. The sun's size also determines its gravitational influence. A larger star would have stronger gravity, pulling planets into closer orbits and potentially making stable, habitable conditions harder to achieve. A smaller star would have weaker gravity, and planets might orbit farther away, receiving less light and heat. The sun's size is just right, providing the conditions that allowed Earth to develop a stable climate and support life. In this sense, the sun's modesty is a gift. The sun's light can be split into a spectrum. When white light from the sun passes through a prism, it splits into a rainbow of colors, from red to violet. This spectrum shows all the wavelengths of visible light that the sun emits. The phenomenon was first studied in detail by Isaac Newton, who demonstrated that white light is not a single color but a mixture of many colors. By recombining the separated colors with another prism, he could produce white light again, proving that the colors were not created by the prism but were already present in the light. The sun's spectrum is not a smooth rainbow. It contains thousands of dark lines, called absorption lines or Fraunhofer lines. These lines are caused by elements in the sun's atmosphere, absorbing light at specific wavelengths. Each element has a unique pattern of absorption lines, like a fingerprint. By studying these lines, astronomers can determine which elements are present in the sun and in what quantities. This technique, spectroscopy, has become one of the most powerful tools in astronomy. Spectroscopy revealed that the sun is composed mostly of hydrogen and helium, with traces of heavier elements like carbon, nitrogen, oxygen, and iron. It also allowed scientists to measure the sun's temperature, density, and even the speeds of gases moving in its atmosphere by observing how the absorption lines shift due to the Doppler effect. The spectrum of the sun is a treasure trove of information, a record written in light that tells us about the star's nature and the processes occurring within it. This same technique is used to study other stars, distant galaxies, and even exoplanets. By analyzing the spectra of light from these objects, astronomers can learn about their composition, temperature, motion, and much more. The Sun, being close and bright, was the perfect subject for developing and refining spectroscopy. Once again, our star served as a laboratory, teaching us techniques that we now apply to the entire universe. The Sun's surface temperature is around 5,500 degrees Celsius. The Sun's photosphere, its visible surface, has a temperature of approximately 5,500 degrees Celsius, or about 10,000 degrees Fahrenheit. This temperature gives the Sun its characteristic white color, though as we've discussed, atmospheric scattering makes it appear yellow from Earth. At this temperature, the Sun emits light across the entire visible spectrum, with a peak in the yellow-green range. Our eyes have evolved to be most sensitive to this range, likely because it is where the Sun emits the most light. Compared to the core, where temperatures reach 15 million degrees Celsius, the photosphere is relatively cool, yet it is still hot enough to vaporize any known material. The temperature drops as you move outward from the photosphere into the chromosphere, and then, paradoxically, rises dramatically in the corona, reaching over 1 million degrees. This temperature inversion is one of the great mysteries of solar physics, and scientists are still working to fully understand the mechanisms that heat the corona to such extreme temperatures. The Sun's surface temperature is determined by the balance between the energy flowing outward from the core and the energy radiated into space. If more energy flows out than is radiated, the surface heats up until equilibrium is restored. If more is radiated than flows out, the surface cools. This balance has been maintained for billions of years, keeping the Sun's surface at a relatively stable temperature. Small variations occur, such as the slightly cooler regions of sunspots, but overall, the photosphere remains consistent. The temperature of a star's surface determines its color and the type of light it emits. Cooler stars, like red dwarfs, have surface temperatures of around 3,000 degrees Celsius and glow with a reddish hue. Hotter stars, like blue giants, can have surface temperatures of 30,000 degrees or more, shining with a brilliant blue-white light. The Sun's temperature places it in the middle, a yellow-white star that provides the right kind of light and heat for life to flourish on Earth. The Sun's light can cause sunburn. While sunlight is essential for life, it also carries dangers. Ultraviolet, UV, radiation, a component of sunlight invisible to the human eye, can damage skin cells. When UV rays penetrate the skin, they can cause DNA mutations, leading to sunburn in the short term and increasing the risk of skin cancer over time. The Earth's ozone layer absorbs much of the most harmful UV radiation, particularly UVC, but UVA and UVB still reach the surface in significant amounts. Sunburn is the skin's response to excessive UV exposure. The skin becomes red, painful, and inflamed as the body's immune system reacts to the damage. Over time, repeated sunburns can lead to premature aging of the skin, wrinkles, and an increased risk of melanoma, a serious form of skin cancer. This is why dermatologists recommend using sunscreen, wearing protective clothing, and seeking shade during the peak sun hours, typically between 10 in the morning and 4 in the afternoon. Different skin types have different levels of natural protection. Melanin, the pigment that gives skin its color, absorbs UV radiation and provides some defense against damage. People with darker skin have more melanin and are less likely to burn, though they are not immune to the harmful effects of UV. People with lighter skin have less melanin and burn more easily. requiring greater caution when spending time in the sun. Regardless of skin type, everyone should take precautions to protect themselves from excessive UV exposure. Despite the risks, sunlight in moderation is beneficial. As mentioned earlier, it is necessary for vitamin D production, and it has other positive effects, such as improving mood and regulating circadian rhythms. The key is balance, enjoying the sun's benefits while minimizing the risks. The sun gives life, but it also demands respect. By understanding its effects and taking appropriate precautions, we can safely enjoy the light that has sustained life on Earth for billions of years. The sun's gravity keeps comets in orbit. Comets are icy bodies that orbit the sun, often in highly elliptical paths that take them from the outer reaches of the solar system to the inner planets and back again. When a comet approaches the sun, the heat causes its ice to vaporize, creating a glowing coma, a cloud of gas and dust around the nucleus, and often a tail that points away from the sun. Pushed by the solar wind and radiation pressure, comets have been observed for thousands of years, and their appearances were often seen as omens or portents. The orbits of comets are determined by the sun's gravity. Some comets, called short-period comets, have orbits that take less than 200 years to complete. They originate from the Kuiper Belt, a region beyond Neptune filled with icy bodies. Other comets, long-period comets, have orbits that can take thousands or even millions of years. These come from the Oort cloud, a vast, distant shell of icy objects that surrounds the solar system, reaching halfway to the nearest star. The sun's gravity holds these distant objects in orbit, even though they are billions of miles away. Occasionally, gravitational interactions with passing stars or giant planets can alter a comet's orbit, sending it on a path toward the inner solar system. When this happens, the comet becomes visible from Earth, sometimes growing bright enough to be seen with the naked eye. Famous comets like Halley's Comet and Comet Hale-Bopp have captivated observers throughout history. Comets are time capsules, preserving material from the early solar system. By studying them, scientists can learn about the conditions that existed when the sun and planets were forming. Missions like Rosetta, which landed a probe on Comet 67P, have provided detailed data about cometary composition, revealing water, organic molecules, and clues about the building blocks of life. The sun's gravity brings these ancient objects close, allowing us to study them and learn about our cosmic origins. The sun powers auroras on other planets. Auroras are not unique to Earth. Any planet with a magnetic field and an atmosphere can experience them when charged particles from the solar wind interact with the planet's magnetosphere. Jupiter has spectacular auroras, far more powerful than Earth's. They are driven not only by the solar wind, but also by material from Jupiter's volcanic moon, Io, which constantly spews particles into space. These particles are captured by Jupiter's magnetic field and funneled toward the poles, creating permanent auroral ovals that glow brightly in ultraviolet and infrared light. Saturn also has auroras, visible at its poles. Like Jupiter, Saturn's auroras are influenced by both the solar wind and its own moons, particularly Enceladus, which emits water vapor into space. Uranus and Neptune, despite their great distance from the Sun and their weaker solar wind environment, also have auroras. These are more difficult to observe, but spacecraft and powerful telescopes have detected them, showing that even the outer planets are touched by the Sun's influence. Mars once had a strong magnetic field, but it has since weakened significantly. Today, Mars has only localized magnetic fields in certain regions, and it experiences patchy auroras rather than the grand displays seen on Earth or the gas giants. These auroras are triggered by the solar wind interacting with the planet's thin atmosphere. and the remnants of its ancient magnetic field. Studying Martian auroras helps scientists understand how the planet's magnetic field evolved and what happened to its once thicker atmosphere. Even Venus, which has no global magnetic field, experiences auroral-like glows. The solar wind interacts directly with its atmosphere, creating bright patches of light. These are different from the classic auroras seen on Earth, but they are still driven by the sun's energy. Across the solar system, the sun's influence creates light shows on world after world, each one unique, each one a testament to the power and reach of our star. The sun's energy is the basis of weather patterns. Weather on Earth is driven by the sun's energy. The heating of the Earth's surface creates differences in temperature and pressure, which drive winds, storms, and all the dynamic phenomena we associate with weather. The equator, receiving more direct sunlight, is warmer than the poles. This temperature difference creates large-scale circulation patterns, with warm air rising near the equator and cooler air sinking near the poles. These patterns, combined with the Earth's rotation and the distribution of land and water, create the complex weather systems we experience. Hurricanes, typhoons, and cyclones are all powered by the sun's heat. They form over warm ocean waters, where the sun has heated the surface to at least 26 degrees Celsius. The warm water evaporates, and the rising air creates a low-pressure system. As more air rushes in to fill the void, it begins to spin due to the Coriolis effect. The storm feeds on the warm water, growing in strength, sometimes becoming a massive swirling system, hundreds of kilometers across. When it makes landfall, it loses its energy source and weakens, but not before causing significant damage. Thunderstorms, too, are driven by solar heating. On a warm day, the sun heats the ground, and the warm air rises rapidly, forming towering cumulonimbus clouds. Within these clouds, updrafts and downdrafts create turbulence, separating electrical charges. When the difference becomes large enough, lightning strikes, releasing energy and creating thunder. The sun's energy, stored as heat and moisture in the atmosphere, is released in these dramatic displays. Even gentle breezes and clear skies are shaped by the sun. The daily cycle of heating and cooling creates local winds, while the seasonal changes in sunlight drive the migration of weather patterns. Without the sun, Earth's atmosphere would be still and frozen, with no winds, no storms, no weather at all. The sun is the engine of our planet's atmosphere, turning light into motion, heat into wind, and energy into the ever-changing dance of weather that shapes our daily lives. The sun creates a constant hum in space. The sun is not just a source of light, but also of sound, though we cannot hear it. The surface of the sun vibrates with countless oscillations, driven by convection and acoustic waves bouncing through its interior. These oscillations create waves that ripple through the sun's plasma. If sound could travel through the vacuum of space, we would hear the sun as a deep, constant hum, a combination of thousands of frequencies blending together. These sound waves are much too low for human ears to detect directly. The dominant frequency has a period of about 5 minutes, far below the range of human hearing. But by measuring the Doppler shifts of light from different parts of the sun's surface, scientists can detect these oscillations and study them. This field, Helioseismology, has revealed the internal structure of the sun, showing how sound waves travel through different layers and bounce off boundaries within. The concept of the sun as a musical instrument is fascinating. Different modes of oscillation correspond to different notes, and the sun plays them all at once, creating a complex chord. Some modes penetrate deep into the core, while others remain near the surface. By analyzing the patterns of oscillations, scientists can infer the temperature, density, and composition of the sun's interior, regions that are otherwise impossible to observe directly. In a poetic sense, the sun is singing, a cosmic song that has been ongoing for billions of years. Though we cannot hear it with our ears, we can detect it with instruments and translate it into data that deepens our understanding. The sun's hum is a reminder that the universe is filled with phenomena beyond our immediate senses, waves and vibrations that shape reality in ways we are only beginning to comprehend. The sun's influence extends to the edge of the solar system. The sun's gravitational pull and the solar wind create a bubble of space called the Heliosphere. This bubble extends far beyond the planets, reaching out over 100 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. At the edge of the Heliosphere lies the heliopause, the boundary where the solar wind slows and meets the interstellar medium, the thin gas that fills the space between stars. The Voyager 1 spacecraft crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018. These spacecraft continue to send data back to Earth, revealing what conditions are like at the edge of the solar system and beyond. Even at that immense distance, over 13 billion miles from the Sun, they still feel its gravitational pull. Though weakly, they will remain gravitationally bound to the Sun for thousands of years, even as they drift farther and farther away. The heliosphere acts as a shield, protecting the inner solar system from some of the galactic cosmic rays, high-energy particles that stream through interstellar space. The Sun's magnetic field, carried by the solar wind, deflects many of these particles, reducing the radiation environment near Earth and the other planets. Without this protection, the radiation levels would be higher, posing greater risks to life and to spacecraft traveling through the solar system. The Sun's influence, while weakening with distance, is still present at the very edges of what we consider our solar system. The Oort cloud, a theoretical shell of icy bodies that may extend halfway to the nearest star, is still bound to the Sun's gravity. Everything within this vast region, from the smallest comet to the largest planet, is part of the Sun's domain, held in place by its mass and shaped by its energy. The Sun is not just the center of the solar system. It is the defining presence, the force that gives structure and order to everything around it. The Sun has been a teacher for humanity. Throughout history, the Sun has taught humanity profound lessons. Ancient peoples learned to track its movements, creating calendars and marking the seasons. They discovered that the Sun's position changes throughout the year, rising and setting at different points on the horizon. This knowledge allowed them to predict when to plant and harvest, shaping agricultural societies and enabling civilizations to flourish. The Sun was the first clock and the first calendar, a natural timekeeper that governed daily life. The study of the Sun also led to advances in mathematics and astronomy. Ancient astronomers developed geometric models to explain the Sun's motion across the sky. They calculated the length of the year with remarkable accuracy, a feat that required careful observation and mathematical sophistication. The need to predict solar eclipses drove further refinement of these models, pushing astronomers to develop better tools and techniques. In modern times, the Sun continues to teach us. It has been central to the development of physics, from Newton's laws of motion and gravity to Einstein's theories of relativity. The Sun's spectrum revealed the nature of light and the composition of matter. The puzzle of how the Sun shines led to the discovery of nuclear fusion, one of the fundamental processes in the universe. Every mystery the Sun presents, from the heating of its corona to the dynamics of its magnetic field, challenges scientists and drives innovation. The Sun is also teaching us about other stars. By studying our Sun in detail, we can apply that knowledge to distant stars that we can only observe as faint points of light. The Sun is our laboratory, a nearby example where we can measure, experiment, and learn. The lessons we learn from the Sun help us understand the wider universe, showing us that the processes happening here in our solar system are universal, playing out across the cosmos in countless other star systems. The Sun's light reaches every corner of the solar system, from Mercury, the closest planet, to the distant reaches of the Kuiper Belt and beyond. The Sun's light touches every object in the solar system. On Mercury, the Sun appears over twice as large and more than 6 times as bright as it does from Earth. The surface bakes in temperatures that can exceed 430 degrees Celsius during the day. On the outer planets, like Neptune, the Sun appears as little more than a very bright star, but it is still the dominant source of light, and its gravitational pull still governs the planet's orbit. Even at the distance of Pluto, about 40 times farther from the Sun than Earth, sunlight still arrives, though much diminished. The Sun provides only a fraction of the light that reaches Earth, and Pluto's surface is cold and dim, with temperatures around -200 to 30 degrees Celsius. Yet, that faint sunlight is enough to create a thin atmosphere when Pluto is closer to the Sun in its elliptical orbit, and it is enough to allow spacecraft like New Horizons to photograph the dwarf planet in detail. In the Kuiper Belt and the Oort cloud, the Sun's light is feeble, but it is still there. Comets in these distant regions are frozen, their ice is dormant. But if their orbits bring them closer to the Sun, they awaken, vaporizing and creating the tails that make them visible from Earth. The Sun's reach is vast, extending its influence across billions of miles, touching every object that orbits it, no matter how distant. The solar system is united by the Sun's light and gravity. Every planet, every moon, every asteroid and comet is part of a family held together by our star. The Sun is the center, the source, the anchor. Its light illuminates the darkness, and its gravity keeps everything in motion, creating the dynamic, interconnected system we call home. From the innermost planet to the outermost reaches, the Sun's presence is felt, a constant reminder of the star that gave birth to it all. The Sun's legacy will last for trillions of years. When the Sun finally exhausts its nuclear fuel and becomes a white dwarf, it will not simply vanish. It will continue to exist, a dense, slowly cooling remnant of its former self. White dwarfs cool very slowly, radiating their residual heat over billions and eventually trillions of years. The Sun, as a white dwarf, will glow faintly for an unimaginable span of time, outlasting most of the stars currently shining in the galaxy. Eventually, after countless eons, the white dwarf will cool to the point where it no longer emits visible light. It will become a black dwarf, a cold, dark cinder floating through space. However, the universe is not yet old enough for any black dwarfs to exist. The oldest white dwarfs, remnants of stars that died billions of years ago, are still glowing faintly. The Sun's cooling will take longer than the current age of the universe many times over, but the Sun's legacy extends beyond its physical remnant. The elements it has created through fusion, and those it will scatter into space when it becomes a planetary nebula, will become part of the next generation of stars and planets. The carbon and oxygen forged in the Sun's core will drift through the galaxy, mixing with other material, and one day, they may be incorporated into new worlds, new life. The Sun's atoms will be recycled, continuing the cosmic cycle. In this sense, the Sun is immortal. Though it will die as a star, its essence will live on, scattered across the galaxy, part of the fabric of the universe. Every atom of carbon in your body may have once been part of a star like the Sun. One day, the atoms that make up the Sun will be part of other beings, other worlds, carrying the legacy of our star into the distant future. The Sun's story does not end with its death. It continues, woven into the ongoing story of the cosmos. The Sun is a source of wonder and inspiration. The Sun has inspired humanity since the beginning. It has been worshipped, studied, painted, and written about. It has guided travelers, marked time, and sustained life. It is the most familiar object in the sky, yet it remains mysterious. A star of immense power and complexity. Every sunrise brings a sense of renewal, and every sunset offers a moment of reflection. The Sun is woven into the fabric of human experience, shaping cultures, religions, and sciences. In modern times, as we have come to understand the Sun scientifically, it has not lost its power to inspire. If anything, the knowledge we have gained makes it even more remarkable. The Sun is a nuclear reactor, a magnetic dynamo, a source of light and life. It is both ordinary, one star among billions, and extraordinary, the most important star in our universe. It has been shining for billions of years, and it will shine for billions more, a constant presence in an ever-changing cosmos. The Sun reminds us of our place in the universe. We are inhabitants of a small planet, orbiting an average star in a vast galaxy. Yet, this star is our Sun, the source of everything we know and love. It warms us, lights our way, and makes life possible. In its light, we see not just the physical world, but also the beauty and wonder of existence itself. The Sun is a gift, a daily reminder to appreciate the world around us and to marvel at the forces that sustain us. As we look to the future, the Sun will continue to be central to our lives. We will harness its energy more efficiently, study it more deeply, and perhaps one day venture closer to it than ever before. The Sun is not just an object in the sky. It is a companion, a teacher, and a source of endless fascination. It has been with us from the beginning, and it will be with us as long as we exist. The Sun is, and always will be, our star, and so we rest under the Sun's light. And so, dear listener, our journey through the story of the Sun comes to a gentle close. From the nuclear fires at its core to the faint glow at the edge of the Heliosphere, we have explored the many faces of our closest star. We have seen how it shapes the solar system, drives the weather, and sustains life. We have learned of its past, its present, and its distant future, a story spanning billions of years. The Sun rises each morning, a quiet promise that the world continues. It sets each evening, painting the sky with colors, a reminder of the beauty that surrounds us. In its light, we live our lives. We grow, we learn, we love. The Sun asks nothing in return. It simply shines, steadily, reliably, giving freely of its energy. It is a symbol of constancy in a world of change, a source of warmth in the cold vastness of space. As you lie here, letting your breath fall into a steady rhythm, imagine yourself beneath the Sun. Feel its warmth on your skin. See its light filtering through the trees or dancing on water. Picture the Sun as it truly is, a massive sphere of glowing plasma, held together by gravity, powered by fusion, surrounded by an atmosphere that reaches millions of miles into space. See its granules churning, its magnetic fields dancing, its corona shimmering in the darkness. The Sun has watched over Earth for billions of years. It has seen the first stirrings of life, the rise and fall of countless species, the evolution of humanity. It has been a silent witness to every moment of history, every triumph and tragedy, every sunrise that brought hope, and every sunset that brought peace. And it will continue, long after we are gone, shining its light on whatever comes next, a steadfast guardian in the cosmic night. As the day gives way to night, every waking thought drifts gently into sleep. The sun sets, but it will rise again, as it always has, as it always will. Let that thought carry you into rest. Close your eyes, breathe deeply, and drift into sleep, into stillness, into the warm embrace of the sun's eternal light. Good night.